If you like the space and learn about its curiosities, consider subscribing to the channel. We have 2 videos every week. Thank you for your attention and enjoy the video. In the realm of recent astronomical discoveries, 2024 has been an exceptionally thrilling year, unveiling new worlds and deepening our understanding of the cosmos. Among the most groundbreaking revelations are the detection of a super-Earth in the habitable zone, an eccentric planet on its way to becoming a hot Jupiter, and the observation of one of the most distant and ancient galaxies, GN-Z11. A notable discovery this year is the super-Earth known as TOI 715b, located approximately 137 light-years away. This planet orbits a red dwarf star, making it a promising candidate for further study regarding the potential for life beyond Earth. TOI 715b is about 1.5 times the size of Earth and resides in what scientists refer to as the conservative habitable zone, a region around a star where conditions might allow liquid water to exist on the planet's surface. This discovery by NASA's Transiting Exoplanet Survey satellite, TESS, and subsequent observations using the James Webb Space Telescope, JWST, aim to uncover whether this planet has an atmosphere, which would be crucial in determining its habitability. If it does possess an atmosphere, the JWST may be able to analyze its composition, potentially identifying elements or molecules that suggest the presence of biological activity. This finding adds to the growing list of Earth-like planets in similar orbits around their stars, raising hopes for finding habitable worlds in our galactic neighborhood. Another fascinating find involves a highly eccentric planet, TC241249530b, discovered by researchers using TESS. This planet, initially a cold, distant world, is undergoing a transformation that will eventually turn it into a hot Jupiter. Such planets are gas giants that orbit very close to their stars, with extreme surface temperatures. TSE241249530b currently follows a highly elliptical orbit, swinging close to its star before being flung back out into space. This dramatic journey suggests that the planet is in the early stages of what astronomers call high eccentricity migration, a process where a planet's orbit becomes highly stretched before eventually stabilizing into a close, circular orbit around its star. In approximately 1 billion years, TSE241249530b is predicted to complete this transformation, becoming a fully developed hot Jupiter. Observations like this are crucial as they provide direct evidence supporting the theory that some hot Jupiters form through these extreme orbital dynamics, reshaping our understanding of planetary evolution. The James Webb Space Telescope has also been pivotal in expanding our view of the universe's distant past. One of the most extraordinary observations this year has been the detailed study of the galaxy GN-Z11, one of the youngest and most distant galaxies ever seen, located roughly 13.4 billion light-years from Earth. Initially detected by the Hubble Space Telescope, GN-Z11 has become a focal point for Webb's near-infrared camera, NIRCam, and near-infrared spectrograph, NIRSpec. This galaxy existed when the universe was just 430 million years old, and it hosts a central supermassive black hole that is actively accreting matter. This discovery sets a new record for the farthest active black hole ever observed. Researchers have also detected a pristine gas clump near the galaxy, likely composed of helium, which is a signature element from the universe's early epochs. The presence of such unpolluted gas suggests that the region might be ripe for the formation of population 3 stars, the universe's first generation of stars, which are thought to have been massive, hot, and short-lived. These findings offer a glimpse into the formation of structures in the early universe, revealing how galaxies and stars began to organize themselves from the primordial chaos following the Big Bang. The ability of Webb to observe these distant objects with unprecedented detail is revolutionizing our understanding of how galaxies evolve and how early cosmic conditions set the stage for the universe we observe today. The hunt for exoplanets also took an exciting turn with the confirmation of LHS 475b, an Earth-sized planet orbiting a red dwarf star just 41 light-years away. Using Webb's near-infrared spectrograph, NIRSpec, researchers confirmed this rocky planet's presence with incredible precision, establishing it as one of the most promising targets for future atmospheric analysis. While it is not yet known if LHS 475b has an atmosphere, its location and size make it an ideal candidate for studying Earth-like environments beyond our solar system. These discoveries collectively illustrate the diversity and complexity of planetary systems and the dynamic processes shaping them. They also highlight how modern telescopes, particularly the James Webb Space Telescope, are pushing the boundaries of what we can learn about distant worlds and the universe's formative years. As technology continues to advance, it's becoming increasingly clear that we are on the brink of uncovering even more profound insights into the cosmos, potentially answering the age-old question of whether we are alone in the universe. The 2024 astronomical landscape is thus rich with discovery and potential, as new observations challenge and refine our understanding of planetary formation, the early universe, and the conditions that might make other worlds habitable. From studying eccentric orbits that transform distant planets into hot Jupiters to peering into the earliest galaxies ever formed, astronomers are weaving a more comprehensive narrative of our universe's history, laying the groundwork for future explorations and discoveries that may one day lead us to find life beyond Earth. In the realm of recent astronomical discoveries, 2024 has been an exceptionally thrilling year, unveiling new worlds and deepening our understanding of the cosmos. Among the most groundbreaking revelations are the detection of a super-Earth in the habitable zone, an eccentric planet on its way to becoming a hot Jupiter, and the observation of one of the most distant and ancient galaxies, GN-Z11. A notable discovery this year is the super-Earth known as TOI 715b, located approximately 137 light-years away. This planet orbits a red dwarf star, making it a promising candidate for further study regarding the potential for life beyond Earth. TOI 715b is about 1.5 times the size of Earth and resides in what scientists refer to as the conservative habitable zone, a region around a star where conditions might allow liquid water to exist on the planet's surface. This discovery by NASA's Transiting Exoplanet Survey satellite, TESS, and subsequent observations using the James Webb Space Telescope, JWST, aim to uncover whether this planet has an atmosphere, which would be crucial in determining its habitability. If it does possess an atmosphere, the JWST may be able to analyze its composition, potentially identifying elements or molecules that suggest the presence of biological activity. This finding adds to the growing list of Earth-like planets in similar orbits around their stars, raising hopes for finding habitable worlds in our galactic neighborhood. Another fascinating find involves a highly eccentric planet, TSE 241249530b, discovered by researchers using TESS. This planet, initially a cold, distant world, is undergoing a transformation that will eventually turn it into a hot Jupiter. Such planets are gas giants that orbit very close to their stars, with extreme surface temperatures. TSE 241249530b currently follows a highly elliptical orbit, swinging close to its star before being flung back out into space. This dramatic journey suggests that the planet is in the early stages of what astronomers call high eccentricity migration, a process where a planet's orbit becomes highly stretched before eventually stabilizing into a close, circular orbit around its star. In approximately 1 billion years, TSE 241249530b is predicted to complete this transformation, becoming a fully developed hot Jupiter. Observations like this are crucial as they provide direct evidence supporting the theory that some hot Jupiters form through these extreme orbital dynamics, reshaping our understanding of planetary evolution. The James Webb Space Telescope has also been pivotal in expanding our view of the universe's distant past. One of the most extraordinary observations this year has been the detailed study of the galaxy GN-Z11, one of the youngest and most distant galaxies ever seen, located roughly 13.4 billion light-years from Earth. Initially detected by the Hubble Space Telescope, GN-Z11 has become a focal point for Webb's near-infrared camera, NIRCam, and near-infrared spectrograph, NIRSpec. This galaxy existed when the universe was just 430 million years old, and it hosts a central supermassive black hole that is actively accreting matter. This discovery sets a new record for the farthest active black hole ever observed. Researchers have also detected a pristine gas clump near the galaxy, likely composed of helium, which is a signature element from the universe's early epochs. The presence of such unpolluted gas suggests that the region might be ripe for the formation of population 3 stars, the universe's first generation of stars, which are thought to have been massive, hot, and short-lived. These findings offer a glimpse into the formation of structures in the early universe, revealing how galaxies and stars began to organize themselves from the primordial chaos following the Big Bang. The ability of Webb to observe these distant objects with unprecedented detail is revolutionizing our understanding of how galaxies evolve and how early cosmic conditions set the stage for the universe we observe today. The hunt for exoplanets also took an exciting turn with the confirmation of LHS 475b, an Earth-sized planet orbiting a red dwarf star just 41 light-years away. Using Webb's near-infrared spectrograph and IR-SPEC, researchers confirmed this rocky planet's presence with incredible precision, establishing it as one of the most promising targets for future atmospheric analysis. While it is not yet known if LHS 475b has an atmosphere, its location and size make it an ideal candidate for studying Earth-like environments beyond our solar system. These discoveries collectively illustrate the diversity and complexity of planetary systems and the dynamic processes shaping them. They also highlight how modern telescopes, particularly the James Webb Space Telescope, are pushing the boundaries of what we can learn about distant worlds and the universe's formative years. As technology continues to advance, it's becoming increasingly clear that we are on the brink of uncovering even more profound insights into the cosmos, potentially answering the age-old question of whether we are alone in the universe. The 2024 astronomical landscape is thus rich with discovery and potential, as new observations challenge and refine our understanding of planetary formation, the early universe, and the conditions that might make other worlds habitable. From studying eccentric orbits that transform distant planets into hot Jupiters to peering into the earliest galaxies ever formed, astronomers are weaving a more comprehensive narrative of our universe's history, laying the groundwork for future explorations and discoveries that may one day lead us to find life beyond Earth. As we move further into the latest astronomical discoveries of 2024, the focus shifts to some of the most extreme and mysterious objects in the universe: black holes, neutron stars, and the remnants of massive stellar explosions, all of which are reshaping our understanding of astrophysics and cosmic evolution. One of the most astonishing developments this year has been the discovery of a rapidly spinning neutron star, or pulsar, located in a distant galaxy. Using the capabilities of the Chandra X-ray Observatory and data from the European Southern Observatory's Very Large Telescope, astronomers identified this pulsar's extreme rotation rate, clocking in at over 1,000 rotations per second. These rapid rotations generate immense magnetic fields, which emit powerful beams of radiation observable as pulses of light whenever the star's magnetic poles sweep past Earth. Such fast-spinning pulsars, known as millisecond pulsars, are rare and provide crucial insights into the physics of matter under extreme conditions. This particular discovery is especially exciting because it could offer clues about how neutron stars evolve and gain their rapid spin rates, potentially through interactions with companion stars that transfer mass and angular momentum. In the realm of black holes, the James Webb Space Telescope has unveiled new details about intermediate mass black holes, IMBHs, a class of black holes that are theorized but notoriously difficult to detect. These black holes are thought to bridge the gap between stellar mass black holes, which form from collapsing stars, and supermassive black holes, which reside at the centers of galaxies. Recent observations of dense star clusters have revealed evidence of these IMBHs through their gravitational influence on nearby stars. Webb's precision has allowed astronomers to track the motions of stars within these clusters, identifying a small, dense central object that exerts a powerful gravitational pull consistent with an IMBH. This finding is critical because understanding these elusive objects could explain how supermassive black holes form and grow over time, whether they emerge from the merging of smaller black holes or through the direct collapse of massive gas clouds. Parallel to these black hole studies, astronomers have been investigating cosmic jets emitted by quasars, some of the brightest objects in the universe. Quasars are powered by supermassive black holes that consume vast amounts of matter, leading to the formation of luminous accretion disks and powerful jets of particles that travel close to the speed of light. This year, astronomers using the Very Long Baseline Array, VLBA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have mapped these jets in unprecedented detail. By studying their composition and speed, researchers are unraveling the mechanisms behind jet formation and the role these jets play in regulating star formation within galaxies. The jets are believed to drive outflows of gas that can either quench or stimulate star formation, making them crucial actors in galaxy evolution. Another significant area of exploration in 2024 has been the study of gamma-ray bursts, GRBs, the most energetic events in the universe. These bursts, often associated with the collapse of massive stars or the merger of neutron stars, release colossal amounts of energy, observable across billions of light years. New observations from the Fermi Gamma-Ray Space Telescope have identified a unique type of GRB that appears shorter in duration, but far more intense in brightness. This type of burst challenges existing models of GRB classification and suggests the possibility of alternative processes, such as the collision of neutron stars with black holes or the collapse of hypermassive stars. Understanding these violent events is crucial for piecing together the life cycles of stars and the formation of the heaviest elements in the universe. Beyond stellar remnants and black holes, astronomers are also making headway in mapping the cosmic web, the vast network of galaxies and dark matter that forms the large-scale structure of the universe. Using data from the Dark Energy Spectroscopic Instrument, DESI, scientists have been constructing the most detailed three-dimensional map of the universe's structure to date. This map reveals how galaxies are distributed and interconnected through filaments of dark matter, tracing the influence of dark energy that drives the universe's expansion. Observations show that galaxies cluster along these filaments, while vast voids devoid of galaxies stretch between them. Such mapping efforts are not only helping to understand the universe's evolution since the Big Bang, but also providing crucial data for testing theories of dark energy and cosmic inflation. One of the most groundbreaking theoretical advances supported by this mapping is the confirmation of cosmic voids. These enormous empty spaces between galaxy clusters play a critical role in shaping the large-scale structure of the universe. Cosmic voids are expanding faster than their denser counterparts, influenced by the dark energy that accelerates the universe's expansion. Recent studies have shown that these voids could be used as natural laboratories to test alternative models of gravity, potentially offering a way to understand the mysterious nature of dark energy. As 2024 progresses, astronomers are also closely monitoring the dynamics of the solar system, including the ongoing exploration of icy bodies like Europa and Enceladus, moons of Jupiter and Saturn that are prime candidates for harboring life. NASA's Europa Clipper mission, set to launch later this decade, aims to study the ice-covered moon's subsurface ocean in detail. Meanwhile, the Cassini data from Enceladus continues to be analyzed for organic compounds, strengthening the case for hydrothermal activity beneath its icy crust. These missions are not only about exploring our own neighborhood, but also about learning more about similar ice-covered worlds that may exist around distant stars. Finally, the search for extraterrestrial life has taken an innovative turn with the development of advanced biosignature detection techniques. The JWST and ground-based observatories like the Extremely Large Telescope, ELT, are refining methods for detecting potential life markers, such as oxygen, methane, and other organic molecules, in exoplanetary atmospheres. Recent studies suggest that, beyond just searching for these molecules, scientists are considering how they interact with each other under various conditions, which could provide a more accurate indication of life. For example, the simultaneous presence of methane and carbon dioxide without carbon monoxide could strongly suggest biological activity, as these gases should naturally react and cancel each other out unless continuously replenished by life forms. In summary, the latest astronomical findings in 2024 encompass a wide range of cosmic phenomena, from the behavior of black holes and neutron stars to the distribution of galaxies and the quest for life. Each discovery not only expands our understanding of the cosmos, but also raises new questions, fueling the continuous cycle of exploration and discovery. The next steps in these missions promise to be just as revolutionary, as astronomers and astrophysicists utilize cutting-edge technology to delve deeper into the mysteries of the universe, pushing the boundaries of what humanity knows about its place among the stars. Moving further into the astronomical landscape of 2024, attention shifts to the intricate processes governing star formation, the evolution of galaxies, and the emerging frontiers in cosmic observation technologies. This year has seen advances that not only enhance our understanding of the universe's past, but also provide new methods to study its present and future, pushing the boundaries of what was previously possible. In the field of star formation, astronomers using data from the Atacama Large Millimeter/Submillimeter Array, ALMA, have made significant progress in understanding how stars are born within dense molecular clouds. ALMA's precision has allowed researchers to pinpoint the exact regions within these clouds where gravity causes gas and dust to collapse, triggering the formation of protostars. These observations reveal that magnetic fields play a crucial role in regulating the collapse process, helping to either facilitate or hinder star formation, depending on their alignment and strength. The results have shown that the interplay between turbulence, magnetic fields, and gravity is more complex than previously thought, providing deeper insights into the diversity of star formation across different environments. Simultaneously, the study of star clusters has taken a leap forward. Astronomers have employed the Hubble Space Telescope alongside the JWST to observe globular clusters, dense collections of ancient stars orbiting the Milky Way. These clusters are not only remnants from the galaxy's early history, but also serve as laboratories for studying stellar evolution. Recent studies have revealed that some globular clusters contain multiple populations of stars with different chemical compositions, indicating that these clusters have experienced multiple waves of star formation. This finding challenges the traditional view that globular clusters are simple, single-generation star groups, suggesting instead that they have undergone complex evolutionary histories shaped by the accretion of gas and interactions with other galactic structures. At the galactic scale, observations using the European Space Agency's Gaia mission have revolutionized our understanding of the Milky Way structure. Gaia's precise mapping of over 1 billion stars has allowed scientists to trace the galaxy's past interactions with smaller galaxies, providing evidence of past collisions that have shaped the Milky Way's spiral arms and halo. This data has led to the identification of several stellar streams, remnants of dwarf galaxies that were torn apart and absorbed into the Milky Way over billions of years. These findings highlight the dynamic and violent nature of galaxy formation, emphasizing that the Milky Way, like many galaxies, is the product of a complex history of mergers and accretions. 2024 has also been a pivotal year for observing phenomena like gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo, along with the newly operational Kagra Observatory in Japan, have continued to detect ripples in space-time caused by the collision of black holes and neutron stars. These events, known as binary mergers, provide crucial information about the population and distribution of these exotic objects throughout the universe. This year, the collaborative effort of these observatories has resulted in the detection of gravitational waves from a previously unobserved type of event, a possible merger between a neutron star and an intermediate mass black hole. This rare occurrence, if confirmed, would be the first of its kind, shedding light on the elusive intermediate mass black holes and how they interact with other massive objects. On the technological frontier, 2024 has seen the successful deployment of new instruments that enhance our ability to observe the universe in various wavelengths. The launch of the Nancy Grace Roman Space Telescope promises to expand the hunt for exoplanets and dark energy. Equipped with a wide-field infrared survey instrument, the Roman telescope will complement the JWST by surveying vast portions of the sky, identifying thousands of new exoplanets through microlensing events and mapping the distribution of dark matter. Its observations will be crucial in understanding the role of dark energy in the universe's accelerated expansion and in refining cosmological models. In tandem with space-based observatories, ground-based telescopes like the extremely large telescope, YELT, in Chile are pushing the limits of astronomical observation. The YELT, with its massive 39-meter primary mirror, is designed to capture light with unprecedented detail, enabling scientists to directly image exoplanets and study their atmospheres. It will also observe the earliest galaxies, furthering our understanding of how they formed and evolved. This year, preliminary observations from the YELT have already begun to reveal structures within star-forming regions that were previously too faint or small to detect. These observations are expected to revolutionize the field of planet formation, offering a close look at protoplanetary disks, the regions around young stars where planets are born. Another breakthrough in technology comes from advancements in adaptive optic systems. These systems, which correct for the distortion caused by Earth's atmosphere, are becoming increasingly sophisticated, allowing ground-based telescopes to achieve clarity comparable to space-based observatories. The next generation of adaptive optics is now being integrated into facilities like the 30-meter telescope, TMT, enhancing their capabilities to study faint objects, including distant galaxies and faint stellar remnants. This improvement is critical for exploring the nature of dark matter, as astronomers aim to map its distribution by observing its gravitational effects on visible matter. These technological leaps are also being leveraged in the search for extraterrestrial intelligence, SETI. Using the improved sensitivity of new radio telescopes, such as the Square Kilometre Array, SK, researchers are scanning a larger volume of the sky for potential technosignatures, signals that might indicate advanced civilizations. The SK's ability to observe at multiple frequencies simultaneously increases the chances of detecting artificial signals, particularly those that might have been missed by previous surveys. While no definitive signals have been identified so far, the ongoing enhancements in detection methods are raising the odds of finding signs of intelligent life within our galaxy or beyond. Additionally, astronomers are working to refine the methods used for identifying exoplanets with the potential for hosting life. Alongside the JWST, the newly launched aerial mission, focused on studying the atmospheres of exoplanets, aims to characterize hundreds of exoplanets over the next decade. Ariel's goal is to understand the chemical composition of these atmospheres, identifying the presence of water vapor, carbon compounds, and other molecules that could point to habitable conditions or even biosignatures. This comprehensive approach is expected to narrow down the list of worlds that warrant further investigation, focusing the search for life on planets with the most Earth-like characteristics. The astronomical discoveries and technological advancements of 2024 paint an expansive picture of the universe, from the birth and death of stars to the detection of distant planets and the mapping of dark matter. As new instruments come online and existing ones refine their capabilities, the astronomical community stands at the cusp of potentially transformative discoveries. Each piece of data brings humanity closer to uncovering the secrets of the cosmos, including the tantalizing possibility of finding life beyond our world. The continued exploration of these frontiers ensures that the universe remains a dynamic, ever-evolving story, one that scientists are just beginning to tell with unprecedented precision. As we delve further into the astronomical discoveries of 2024, the focus increasingly shifts to the role of fundamental physics and cosmology, pushing the limits of our understanding of the universe's inception, its current structure, and its eventual fate. The integration of cutting-edge technology, along with advances in theoretical models, is leading to unprecedented insights into the nature of dark matter, cosmic inflation, and the interactions between matter and dark energy. A major highlight of 2024 has been the work on detecting and studying dark matter. Despite being one of the most mysterious components of the universe, accounting for about 27% of its mass energy content, dark matter remains undetectable by conventional means as it does not emit, absorb, or reflect light. However, astronomers have made significant strides using the Dark Energy Spectroscopic Instrument, DESI, and gravitational lensing techniques. DESI has been instrumental in mapping dark matter through its influence on visible matter, creating a more comprehensive map of the universe's large-scale structure. By analyzing how light from distant galaxies bends as it passes through dark matter, scientists have refined models that describe the distribution and clumping behavior of this enigmatic substance. In addition, the use of gravitational waves to probe dark matter has shown promising results. The LIGO-Virgo-CAGRA collaboration has begun exploring whether these waves could provide indirect evidence of dark matter. One hypothesis suggests that if dark matter consists of primordial black holes formed in the early universe rather than through stellar collapse, these objects could influence the gravitational wave signals detected when massive objects merge. Early data has shown potential anomalies consistent with this theory, but further observations are required to confirm these findings. If proven, this could radically alter our understanding of dark matter's composition and origin. Theoretical advances in understanding cosmic inflation, the rapid expansion of the universe immediately following the Big Bang, have also taken center stage this year. Researchers are using the Planck satellite's detailed cosmic microwave background (CMB) data alongside new measurements from the South Pole Telescope (SPT) and the Atacama Cosmology Telescope (ACT) to refine models of inflation. The goal is to pinpoint the specific conditions that led to the universe's exponential growth, which set the stage for the cosmic structures we observe today. By comparing data from multiple sources, astronomers are narrowing down the properties of the inflationary field, such as its energy levels and the types of particles involved. This refined model could help reconcile discrepancies between observations of the CMB and predictions made by inflationary theory, moving us closer to a unified understanding of the universe's origins. Another frontier explored in 2024 is the nature of dark energy, the mysterious force that drives the accelerated expansion of the universe. The Nancy Grace Roman Space Telescope, set to be launched later this decade, is poised to study this phenomenon by observing the distribution of galaxies and the brightness of distant supernovae. However, current telescopes are already gathering critical preliminary data. The Hubble Space Telescope, using its Wide Field Camera 3 (WFC3), has tracked several Type Ia supernovae, exploding stars used as standard candles to measure cosmic distances. These measurements provide evidence for the influence of dark energy, refining models that describe how it affects the universe's expansion rate. Simultaneously, researchers are exploring alternative explanations for cosmic acceleration beyond dark energy. One hypothesis involves modifications to Einstein's theory of general relativity, suggesting that gravity itself may behave differently on cosmological scales than currently understood. Observations of large cosmic voids, regions of space largely devoid of galaxies, are being used to test these alternative models. These voids act as cosmic laboratories where deviations from general relativity might be more pronounced due to the absence of significant matter. Preliminary results from these studies show some intriguing anomalies, though further data is needed before any definitive conclusions can be drawn. On the observational front, the James Webb Space Telescope, JWST, continues to be a powerhouse for cosmic discovery. One of its most significant contributions this year has been the identification of extremely young and massive galaxies that existed only a few 100 million years after the Big Bang. These galaxies, observed in detail with the near-infrared camera and IR-CAM, challenge existing theories of galaxy formation by appearing much larger and more developed than expected for such an early stage of the universe. This suggests that the processes driving the formation and growth of galaxies were far more efficient or occurred much earlier than current models predict. Researchers are now revisiting the initial conditions of the early universe to account for these unexpected findings. Moreover, JWST's capabilities have allowed astronomers to observe the first clear evidence of population 3 stars, hypothetical stars made almost entirely of hydrogen and helium, the first elements formed after the Big Bang. Until now, these stars had only been theorized, but JWST has detected their characteristic signatures, such as the specific wavelengths of ionized helium, in the halos of ancient galaxies like GN-Z11. The confirmation of population 3 stars is a groundbreaking achievement, as it provides direct evidence of the early stages of star formation and the chemical evolution that led to the creation of heavier elements necessary for planet and life formation. The quest to find habitable worlds and signs of life has also accelerated. The Ariel mission and the JWST are collaborating on detailed spectroscopic studies of exoplanets' atmospheres. By targeting planets orbiting within the habitable zones of red dwarf stars, these telescopes have already identified several promising candidates with atmospheres containing water vapor and other molecules indicative of potential habitability. One such discovery is a planet similar in size to Earth, but with a thick atmosphere, located in the TRAPPIST-1 system. This planet's atmosphere appears to contain both water vapor and carbon dioxide, making it one of the most compelling candidates for further study. In the search for biosignatures, scientists are refining their methods to detect more subtle indicators of life. For instance, the combination of methane and carbon dioxide without the presence of carbon monoxide, detected in the atmosphere of an exoplanet, would be a strong indicator of biological activity, as these gases should naturally react and balance each other out. Such findings are becoming increasingly feasible with the precision of JWST and future missions like the YELT, which aim to directly image the surfaces of these distant worlds. The 2024 astronomical landscape continues to be a dynamic and transformative period for astronomy and astrophysics. From the search for dark matter and dark energy to the observation of the earliest stars and galaxies, each discovery brings us closer to answering fundamental questions about the universe's structure and evolution. The integration of advanced technologies and innovative theoretical approaches ensures that the next decade will be filled with groundbreaking discoveries, potentially reshaping humanity's understanding of its place in the cosmos. As we continue exploring the vast and transformative astronomical discoveries of 2024, new horizons are being uncovered in the fields of multi-messenger astronomy, planetary science, and the search for extraterrestrial life. This period has been marked by innovative research techniques and collaborations that merge different branches of astrophysics, offering comprehensive insights into some of the most compelling phenomena in the universe. One of the most exciting areas of progress has been in multi-messenger astronomy, where observations across various spectra, such as gravitational waves, electromagnetic waves, neutrinos, and cosmic rays, are combined to provide a fuller picture of cosmic events. The Laser Interferometer Gravitational Wave Observatory, LIGO, Virgo, and the New Cagra Observatory have collaborated extensively to detect binary mergers. This year, these facilities recorded a particularly notable event: the simultaneous observation of gravitational waves and high-energy neutrinos from the merger of a neutron star and a black hole. This groundbreaking detection offers a glimpse into how these massive collisions not only warp space-time, but also generate streams of particles that travel across the universe. Multi-messenger approaches are crucial because they allow astronomers to cross-reference data from different observatories, confirming and refining models of these extreme astrophysical processes. In planetary science, recent missions and telescopic observations have brought new insights into the moons of the gas giants, highlighting their potential for harboring life. Europa and Enceladus, moons of Jupiter and Saturn respectively, remain prime candidates due to their subsurface oceans. The Cassini mission data from Enceladus, still being analyzed years after its conclusion, has revealed the presence of organic molecules in the plumes erupting from the moon's icy crust. These organic compounds are consistent with the basic building blocks of life, indicating that hydrothermal activity is likely occurring beneath the ice, where water interacts with rock to produce chemical reactions that could sustain microbial life. The upcoming Europa Clipper mission is set to launch in the latter half of this decade and will further investigate these promising environments. It aims to fly through the plumes of Europa, collecting and analyzing material that could reveal more about the moon's habitability. The combination of data from Cassini and the soon-to-launch Europa Clipper will provide a comparative analysis of these two ocean worlds, helping scientists determine whether life could indeed emerge in such environments, isolated beneath thick layers of ice, but sustained by internal heat and chemical processes. Back on Earth, Astronomers are leveraging these extraterrestrial findings to refine astrobiological models. They are studying extreme environments such as Earth's deep sea, hydrothermal vents, and icy Antarctic lakes as analogs for these moons, searching for microbial communities that could thrive under similar conditions. These Earth-based studies are instrumental in developing detection techniques for potential life forms beyond our planet, informing the design of future missions to icy moons and other promising targets like Mars and Titan. In the search for habitable exoplanets, 2024 has seen the James Webb Space Telescope, JWST, and the upcoming aerial mission take center stage in studying the atmospheres of distant worlds. The JWST's detailed infrared spectroscopy has allowed for the identification of specific molecules in the atmospheres of several exoplanets within the habitable zones of their stars. This year, researchers reported the detection of water vapor, methane, and other organic compounds in the atmosphere of a super-Earth orbiting a red dwarf star in the TRAPPIST-1 system. These findings are crucial because they align with the conditions necessary for life as we know it, making these planets prime candidates for further investigation. The aerial mission, which will join the JWST in studying exoplanets, aims to build a comprehensive database of atmospheric compositions across hundreds of planets. By analyzing the chemical makeup of these atmospheres, scientists hope to identify planets where the balance of gases might indicate biological activity. This broad survey approach will enable researchers to categorize planets by their potential for habitability, focusing future missions on the most promising candidates. The synergy between JWST's detailed observations and Ariel's extensive survey capabilities is expected to revolutionize our understanding of the diversity of planetary atmospheres and their capacity to support life. Another fascinating development this year has been the further exploration of rogue planets, planetary bodies that do not orbit any star and instead drift through interstellar space. The Nancy Grace Roman Space Telescope and Gaia mission have collaborated to identify these free-floating planets through gravitational microlensing events, where the rogue planet's gravity bends the light of background stars as it passes by. These observations are important as they provide a unique opportunity to study planet formation and evolution in environments outside of traditional planetary systems. By understanding the characteristics of these rogue planets, astronomers can gain insights into how planets form, migrate, and sometimes escape the gravitational pull of their parent stars. Advances in technology have also played a pivotal role in shaping 2024's discoveries. The Extremely Large Telescope, ELT, in Chile has begun its initial observations, leveraging its massive mirror to directly image protoplanetary disks around young stars. These disks are the birthplaces of planets, and the ELT's resolution has allowed astronomers to observe the early stages of planet formation, including the accumulation of dust and gas that leads to the development of planetesimals. This high level of detail offers the chance to test planet formation theories directly, comparing simulations with real-world observations to refine our models of how planets, including those like Earth, come into existence. The rise of next-generation adaptive optic systems has also improved ground-based observations, bringing them closer to the clarity of space-based telescopes like the JWST. The 30-meter telescope, TMT, and other observatories now equipped with these systems are focusing on faint exoplanets and distant galaxies. These technological improvements are essential for mapping the distribution of dark matter through galaxy clustering and gravitational lensing studies, helping astronomers better understand how this invisible component influences cosmic evolution. Looking ahead, the astronomical community is eagerly anticipating the launch of several missions designed to probe the early universe and refine our understanding of cosmic origins. Projects like the Square Kilometer Array (SK) are set to provide new insights into the universe's dark ages, a period before the first stars formed, by detecting the faint signals of neutral hydrogen that pervaded the cosmos at that time. The SK's unprecedented sensitivity will allow scientists to map the emergence of structure in the early universe, tracing the transition from a dark, featureless expanse to the luminous, complex cosmos filled with stars and galaxies. The discoveries and technological advancements of 2024 illustrate the interconnected nature of astronomical research, as new tools and methods reveal the universe's secrets across multiple domains. From the birth of stars and planets, to the search for life and the mapping of cosmic structures. As humanity continues to push the boundaries of space exploration and observation, each breakthrough not only enriches our scientific understanding, but also brings us closer to answering the fundamental questions about the origins, evolution, and diversity of the universe we inhabit. Continuing the exploration of 2024's astronomical advancements, we find that the collaboration between observational technologies and theoretical models has reached new heights, leading to transformative discoveries in the understanding of black holes, the origins of the universe, and the search for alien life. In the realm of black hole research, 2024 has been particularly groundbreaking. The Event Horizon Telescope, EHT, which captured the first image of a black hole in 2019, has now unveiled its most detailed image of the supermassive black hole at the center of the Milky Way, Sagittarius A star. This new image shows unprecedented clarity in the accretion disk, an immense, spinning disk of superheated gas and dust that surrounds the event horizon. The observations have revealed patterns in the magnetic fields that are key to understanding how material flows into black holes and how these massive objects emit powerful jets of energy across vast distances. By studying these jets and their origins, astronomers can better grasp the mechanisms that regulate the growth of black holes and influence the evolution of galaxies. Further black hole studies have benefited from the ongoing data collection by the James Webb Space Telescope, JWST. Using its near-infrared spectrograph, NIR-SPEC, the JWST has detected signs of intermediate-mass black holes, IMBHs, within globular clusters. These IMBHs, which are smaller than supermassive black holes but much larger than stellar-mass black holes, have long been theorized but rarely observed directly. The JWST's capabilities allow astronomers to track the motions of stars influenced by these hidden giants, providing crucial evidence of their existence and insights into how such black holes may merge to form even larger ones. Understanding IMBHs is fundamental to piecing together the puzzle of how supermassive black holes, like those at the centers of galaxies, develop over cosmic time. Cosmology has also made significant strides this year, particularly in refining our understanding of cosmic inflation and the structure of the early universe. The European Space Agency's ESA Planck satellite, in conjunction with data from the South Pole Telescope, SPT, and the Atacama Cosmology Telescope, ACT, continues to provide detailed maps of the cosmic microwave background, CMB, the afterglow of the Big Bang. These maps reveal subtle variations that correspond to fluctuations in the density of matter in the early universe. By comparing these patterns with simulations of inflationary models, cosmologists are gaining clearer insights into the conditions that led to the rapid expansion of the universe immediately after its inception. The latest results suggest that inflation was driven by a complex scalar field that not only caused rapid expansion, but also influenced the distribution of dark matter in galaxies that formed much later. One of the most ambitious projects in this field is the Euclid mission, launched by ESA, which aims to map the universe's dark matter and dark energy distributions with unprecedented precision. As Euclid collects data, it will create a three-dimensional map of galaxies spread across billions of light-years, providing critical evidence for testing models of dark energy. Early results from this mission have already begun to refine the parameters of dark energy's influence on cosmic expansion, showing slight but significant deviations from previous estimates. These findings are crucial for improving our understanding of the universe's fate, whether it will expand forever, gradually slow down, or collapse back into a singular state. In the ongoing search for extraterrestrial life, 2024 has been a pivotal year. The collaboration between JWST and aerial missions has focused on characterizing exoplanet atmospheres, targeting worlds that show signs of habitability. Recently, these telescopes observed a super-Earth in the habitable zone of its star, where the JWST detected the presence of water vapor and carbon-based molecules, indicating the possibility of a temperate environment similar to Earth's. Such findings are not just tantalizing. They represent a major step forward in the search for biosignatures, as these molecules are crucial components of organic life. Complementing these efforts, the Square Kilometre Array (SK), which is being constructed to become the world's largest radio telescope, has expanded the search for technosignatures, signals, or traces of advanced civilizations. SK's array of thousands of antennas will allow astronomers to scan vast regions of the sky simultaneously across multiple frequencies, increasing the likelihood of detecting artificial signals that previous searches might have missed. This advanced capability aims to answer one of the most profound questions: whether intelligent life exists elsewhere in the cosmos. Another key area of planetary science has been the study of rogue planets, those not bound to any star. The Gaia mission, which focuses on astrometric measurements, has identified dozens of such planets through microlensing events. These observations provide clues about planetary formation processes, suggesting that rogue planets might be ejected from their star systems through gravitational interactions or collisions with other massive bodies. The discovery of these planets, some of which are similar in size to Earth, raises fascinating questions about whether they could host subsurface oceans or atmospheres that might support life, even without the warmth of a star. At the same time, Earth-based analog studies continue to play a crucial role in astrobiology. By exploring extreme environments such as deep-sea hydrothermal vents and the icy subsurface lakes in Antarctica, scientists gain insights into how life could potentially exist under similar conditions on other planets and moons. The study of extremophiles, organisms that thrive in these hostile environments, helps refine the models used to predict what forms of life might be found on moons like Europa and Enceladus or beneath the surface of Mars. This year's advancements also include the implementation of advanced laser-based technology for planetary exploration, particularly for Mars missions. NASA's Mars Sample Return mission has started testing a new laser ablation technique that allows rovers to analyze rock compositions from a distance. This technology could be pivotal for identifying biosignatures directly on the Martian surface or detecting mineral deposits that indicate past water activity. By combining these techniques with remote sensing data, scientists are building a comprehensive strategy for investigating Mars's past habitability. The interplay between observational advancements and theoretical breakthroughs defines the astronomical discoveries of 2024, bridging the gap between past cosmic events and future explorations. Each technological innovation, from advanced telescopes to space missions and Earth-based simulations, deepens humanity's understanding of the universe's complex processes. These efforts not only expand our knowledge, but also prepare the groundwork for future missions aimed at finding life and unraveling the mysteries of the cosmos. As the year progresses, the astronomical community remains poised for even more revolutionary discoveries that will continue to redefine our place in the universe. As 2024 progresses, the frontiers of astronomy and astrophysics continue to be pushed further, with groundbreaking discoveries in cosmic evolution, planetary systems, and technological advancements that are opening new windows into the universe's most profound mysteries. One of the most impactful areas of study has been in understanding cosmic magnetism and its role in shaping galaxies, stars, and planets. Utilizing the Square Kilometre Array (SK) in its initial phase, astronomers have begun to map the magnetic fields across our galaxy and beyond. These observations show that magnetism is not just a peripheral force but a fundamental aspect that influences star formation, galaxy evolution, and even the behavior of cosmic dust. The data reveals that magnetic fields are intricately woven through the interstellar medium, shaping how gas clouds collapse to form stars and how galactic structures emerge and sustain themselves over billions of years. These findings are corroborated by studies from the Atacama Large Millimeter/Submillimeter Array (ALMA), which have captured the polarization of light emitted by cold dust grains in star-forming regions. This polarization is influenced by magnetic fields, and the patterns observed provide clues about the alignment and intensity of these fields within molecular clouds, the birthplaces of stars. By combining these observations with data from the SK, astronomers are refining models that explain how magnetic fields influence the early stages of star formation, showing that they play a critical role in channeling material into dense filaments where stars eventually form. Meanwhile, the study of cosmic rays, high-energy particles that travel through space, has reached new heights. The Pierre Auger Observatory and the IceCube Neutrino Observatory have collaborated to trace the origins of these particles, revealing that many of them are accelerated by supernova remnants and active galactic nuclei, AGN. Recent discoveries include the detection of ultra-high-energy cosmic rays, which appear to be linked to massive black holes at the centers of distant galaxies. This connection suggests that black holes are not only engines of cosmic evolution through their influence on galaxy formation, but also through their ability to accelerate particles to near-light speeds, contributing to the cosmic energy landscape. In planetary science, the development of new methods for detecting and studying exoplanets has transformed the field. The Transiting Exoplanet Survey Satellite, TESS, and JWST have discovered a number of new exoplanets that challenge our understanding of planetary systems. This year, they identified several water worlds, planets that may have global oceans under thick atmospheres. These planets are intriguing because they reside in their stars' habitable zones and show spectral signatures consistent with the presence of water vapor and other volatile compounds. Such findings are reshaping our criteria for habitability, suggesting that life could emerge in environments far different from Earth's, such as beneath the ice of a water world's ocean. These discoveries are enhanced by the launch of the James Webb Space Telescope's, JWST, sister missions like Plato, planetary transits, and oscillations of stars, which aim to find Earth-like planets around Sun-like stars. Plato's mission is to observe a large area of the sky for extended periods, detecting the subtle dimming that occurs when planets pass in front of their stars. The combined data from Plato and JWST will allow for the most detailed analysis of planetary atmospheres to date, increasing the chances of identifying biosignatures, gases and compounds that could indicate the presence of life. Further advancements in technology have also enabled more detailed studies of our own solar system's past. NASA's Perseverance rover continues its exploration of Mars, collecting and preparing samples for the Mars Sample Return mission. This mission, in collaboration with the European Space Agency, ESA, aims to bring Martian soil and rock samples back to Earth for analysis. Scientists hope that these samples will reveal past signs of microbial life, as well as clues about the planet's geological history and climate evolution. The samples could confirm whether Mars once had conditions suitable for life, providing a direct link between planetary processes and the development of life. Closer to home, the study of Earth-like analogs, such as Antarctica's subsurface lakes and deep-sea hydrothermal vents, remains crucial for refining astrobiological models. These environments host extremophiles, organisms that thrive under extreme conditions, and serve as proxies for studying potential habitats on other planets and moons. The insights gained from these Earth analogs are informing the design of missions targeting icy moons like Europa and Enceladus, where similar conditions might exist beneath thick ice layers. Moreover, the study of Earth's own atmosphere and its interactions with space weather has gained new importance. The Parker Solar Probe and the Solar Orbiter missions are providing real-time data on solar wind and coronal mass ejections, CMEs, which impact Earth's magnetosphere. Understanding these interactions is crucial for protecting satellites, power grids, and other technology on Earth from the effects of intense solar activity. The data collected is also shedding light on how solar radiation and magnetic fields influence atmospheric chemistry, which has implications for understanding similar processes on other planets. Looking ahead, the development of the Lunar Gateway, an international space station orbiting the Moon, will play a key role in expanding human exploration and research beyond Earth's orbit. Scheduled for completion later this decade, the Gateway will serve as a hub for lunar missions and a staging point for future Mars exploration. Its laboratories will facilitate research on space weather, cosmic radiation, and the effects of microgravity on biological systems, all essential for long-term human missions beyond Earth. The Gateway represents not only a leap forward in space exploration, but also a platform for developing technologies that will enable sustainable human presence on other planetary bodies. As 2024 continues, the advancements in astronomical research and technology demonstrate humanity's growing capacity to explore and understand the cosmos. Each discovery, from the mapping of cosmic magnetic fields to the search for life on distant planets, builds a more intricate picture of the universe's complexity. These efforts, driven by a combination of ground-based observatories, space missions, and international collaborations, promise to bring us closer to answering some of the most profound questions about the nature of the universe, the origins of life, and the future of human exploration beyond Earth. Continuing into the discoveries and technological advancements of 2024, astronomy's trajectory remains aimed at unraveling both the grand-scale structures of the universe and the intricate details of planetary environments. These new insights bridge the past and future of cosmic evolution, while humanity's aspirations in space exploration take bold steps forward. A central focus has been on the study of gravitational waves and their impact on understanding the universe's structure. The LIGO-Virgo-Cagra network, now more advanced with upgraded detectors, has captured some of the most detailed waveforms from binary black hole mergers and neutron star collisions. These waves provide astronomers with a direct view of the universe's most violent events, enabling them to test the predictions of general relativity under extreme conditions. Recent observations have identified a neutron star-black hole merger, marking a significant milestone as it offers the opportunity to observe how these two vastly different objects interact. This event has deepened our understanding of how elements like gold and platinum are forged in the universe, as such collisions are thought to be key sources of heavy element production. Meanwhile, the James Webb Space Telescope, JWST, has delivered stunning observations of the universe's early days. One of its major accomplishments this year has been the observation of galaxies that formed within the first 300 million years after the Big Bang. These galaxies appear far more massive and structured than previously expected, suggesting that galaxy formation might have occurred at a much faster rate during the universe's infancy than models have predicted. Researchers are now exploring whether these early galaxies had access to reservoirs of cold gas that fueled their rapid growth, or if they formed through the mergers of smaller, primordial structures. In terms of solar system exploration, the exploration of the Moon is gaining renewed attention as part of NASA's Artemis program. The upcoming Artemis 3 mission is scheduled to be the first crewed lunar landing since the Apollo era, with plans to set up a sustainable presence on the Moon's surface. The mission will include the construction of a lunar base camp and the testing of new technologies aimed at long-term habitation, such as oxygen production from lunar regolith and advanced life support systems. These developments are crucial stepping stones for future Mars missions, as they test the hardware and strategies needed for extended human operations on another planetary body. Beyond the Moon, Mars exploration remains a major focus. The Perseverance rover has continued its exploration of Jezero crater, analyzing rock samples that could hold clues to ancient Martian life. Its findings suggest that the crater's lakebed might have hosted stable water conditions for longer periods than previously thought, increasing the chances that microbial life could have thrived there billions of years ago. The rover's work is part of the larger Mars Sample Return Mission, an international collaboration between NASA and the European Space Agency, ESA, aimed at bringing Martian samples back to Earth for detailed laboratory analysis. These samples could confirm whether Mars ever hosted life, offering a historic breakthrough in our search for extraterrestrial biology. Simultaneously, the study of icy moons in the outer solar system has ramped up, particularly with the planned Europa Clipper mission. This mission will explore Jupiter's moon Europa, which is believed to have a vast subsurface ocean beneath its ice crust. The Clipper aims to fly through the plumes of water vapor erupting from Europa's surface to collect and analyze material that may contain signs of microbial life or organic compounds. This effort will be complemented by ESA's Jupiter Icy Moons Explorer, JUICE, which will study both Europa and Ganymede, another of Jupiter's moons that is suspected to harbor an underground ocean. Together, these missions aim to determine whether these ocean worlds could support life and to prepare for potential future landings. The search for habitable exoplanets has also accelerated, with the JWST leading the way in characterizing exoplanet atmospheres. Observations of planets orbiting in the habitable zones of nearby stars, particularly red dwarfs, have revealed atmospheres rich in water vapor and methane, elements that are crucial markers in the search for life. However, the presence of these compounds alone is not enough. Astronomers are now focusing on the ratios and interactions of these gases to determine if they are being maintained by biological processes. For instance, the detection of both oxygen and methane in an exoplanet's atmosphere could be a strong indicator of life, as these gases would normally react and neutralize each other unless continuously replenished by biological activity. Technology continues to evolve, enabling more refined observations and increasing the precision of planetary studies. The upcoming launch of the Extremely Large Telescope, ELT, is poised to revolutionize exoplanet research. With a 39-meter mirror, the ELT will be the largest optical/infrared telescope ever built, capable of directly imaging exoplanets and studying their atmospheres in greater detail than ever before. Its capabilities are expected to complement the JWST's work, allowing astronomers to identify potential biosignatures and analyze planetary environments at unprecedented scales. New efforts are also being directed towards studying the nature of dark matter and dark energy, two of the universe's most elusive components. The Euclid mission, launched by the European Space Agency, is specifically designed to map the dark universe by observing the distribution of galaxies and cosmic structures. By measuring how light from distant galaxies is distorted by dark matter, Euclid aims to construct a 3D map that reveals how dark matter and dark energy influence the cosmos. This data will refine our understanding of the universe's expansion and provide crucial tests for alternative theories of gravity, challenging or confirming Einstein's theory on a cosmic scale. In addition, adaptive optic systems have reached new levels of sophistication, particularly in ground-based observatories like the 30-meter telescope, TMT. These systems counteract the blurring effect of Earth's atmosphere, allowing astronomers to achieve clarity that rivals space-based observatories. This technological leap is crucial for observing faint, distant galaxies, star-forming regions, and the atmospheres of exoplanets with more precision than ever before. The improved resolution is helping to map the influence of dark matter around galaxies and study the processes that govern star and planet formation. Looking ahead, humanity's expanding reach in space exploration is set to reshape our understanding of both our own solar system and distant worlds. The development of the Lunar Gateway, a planned space station in orbit around the Moon, will serve as a platform for lunar and Mars missions. It will provide the infrastructure necessary for long-term human presence beyond Earth, supporting research into the effects of microgravity, space radiation, and lunar resources. This station is not only a stepping stone for Mars exploration, but also a critical hub for international cooperation in space, involving agencies like NASA, ESA, Roscosmos, and others. The discoveries and technological innovations of 2024 continue to expand humanity's grasp of the universe. From understanding the early universe's rapid development and the dynamics of black holes to exploring our solar system and searching for life on distant worlds. Each step taken this year builds towards a comprehensive, interconnected picture of cosmic evolution. The integration of advanced observational tools, international missions, and cutting-edge theoretical models ensures that the next phase of exploration will be as transformative as it is revealing, marking a pivotal era in our quest to uncover the secrets of the cosmos. As 2024 advances, the astronomical discoveries continue to delve into even more profound and intricate areas, such as the origins of cosmic structures, the advancement of human missions, and the expansion of the search for extraterrestrial life. The developments this year are both transformative and foundational, setting the stage for future explorations and studies that could redefine humanity's understanding of its place in the cosmos. One of the major achievements this year has been the enhanced understanding of cosmic web formation, the vast, interconnected network of galaxies, dark matter, and gas that forms the universe's large-scale structure. By combining observations from the Dark Energy Spectroscopic Instrument, DESI, and simulations from the illustrious TNG project, astronomers have managed to create detailed three-dimensional maps of the cosmic web. These maps reveal the intricate filaments and nodes where galaxies cluster, tracing the paths shaped by dark matter's gravitational influence. This improved view allows researchers to test theories of cosmic evolution, particularly how dark matter and dark energy have influenced the universe's expansion and structural formation since the Big Bang. The study of cosmic voids, large, empty regions within the cosmic web, has become a focal point as well. These voids, largely free of galaxies and matter, are expanding faster than denser regions and provide unique environments to test alternative models of gravity. Recent findings from DESI indicate that these voids may behave differently than expected under standard cosmological models, suggesting the potential for new physics or a re-evaluation of dark energy's properties. By using voids as cosmic laboratories, astronomers hope to uncover more about the universe's acceleration and whether other forces beyond dark energy might be at play. Simultaneously, the James Webb Space Telescope, JWST, has achieved breakthroughs in understanding the earliest galaxies. This year, it identified and analyzed several protoclusters of galaxies forming just a few 100 million years after the Big Bang. These protoclusters represent the universe's first attempts at forming large-scale structures and provide insight into the processes that initiated galaxy formation. JWST's advanced spectroscopy capabilities have allowed astronomers to study the chemical composition and star formation rates within these young clusters, showing that heavy elements and star-forming regions were more abundant at earlier cosmic times than previously thought. On the frontier of human space exploration, 2024 has seen considerable progress toward building a sustainable human presence beyond Earth's orbit. The Artemis program, spearheaded by NASA with international partners, is on track for its first crewed lunar landing in over 50 years. Artemis 3, set to land on the Moon's south pole, aims to establish a permanent foothold that will support future missions and act as a testing ground for technologies essential for Mars exploration. This mission will deploy new habitats, solar power arrays, and life support systems designed to withstand the Moon's harsh environment. The success of Artemis 3 is critical as it sets the stage for a continuous human presence on the Moon and lays the groundwork for the upcoming Mars missions planned for the 2030s. The Lunar Gateway, a collaborative effort involving NASA, ESA, Roscosmos, and other international space agencies, is also making strides. Designed to orbit the Moon, the Gateway will serve as a support station for lunar missions, offering laboratories and docking facilities for crewed and robotic spacecraft. This platform is crucial for extending human activities beyond low Earth orbit and will play a key role in missions aimed at exploring deeper into the solar system. The Gateway's development represents a significant step towards sustainable, long-term space habitation, enabling more complex lunar operations and serving as a stepping stone for crewed Mars missions. Mars exploration continues to be a centerpiece of international space efforts. The Mars Sample Return Mission, a joint endeavor between NASA and ESA, is progressing with plans to retrieve soil and rock samples collected by the Perseverance rover. These samples are expected to provide definitive evidence of past Martian environments, including whether microbial life could have existed on the Red Planet. Such a discovery would be transformative, offering the first direct evidence of extraterrestrial life and fundamentally altering our understanding of biology beyond Earth. In the outer solar system, the focus on icy moons has intensified. NASA's upcoming Europa Clipper mission is designed to explore the possibility of life beneath Europa's icy shell. Scheduled for launch in the late 2020s, the Clipper will perform multiple flybys of Europa, analyzing the Moon's surface, ice composition, and plumes of water vapor that erupt from its subsurface ocean. This mission builds on discoveries from the Galileo spacecraft, which provided early evidence of a vast, salty ocean beneath Europa's ice. If the Clipper detects organic molecules or signs of hydrothermal activity, it could provide compelling evidence for life in the solar system beyond Earth. Parallel to these missions, advancements in exoplanet detection and study continue to grow. The European Space Agency's Plato mission, launched to observe thousands of stars and their planets, aims to discover Earth-like exoplanets around Sun-like stars. Plato's broad field of view and sensitive instruments are expected to increase the catalog of potentially habitable worlds. Together with the JWST and future missions like the Extremely Large Telescope, YELT, these observatories will provide the necessary data to characterize exoplanet atmospheres, seeking conditions that could indicate the presence of liquid water and organic molecules necessary for life. The search for technosignatures, artificial signals that could indicate advanced civilizations, has also expanded, thanks to the improved capabilities of the Square Kilometre Array (SK). This massive radio telescope, still under construction, has already begun its initial operations, scanning the skies for unusual radio emissions. Its ability to observe a vast range of frequencies and cover large portions of the sky simultaneously makes it the most powerful tool yet in the hunt for extraterrestrial intelligence. If detected, such signals would provide the most compelling evidence of intelligent life beyond Earth, prompting an unprecedented shift in humanity's perspective on its place in the universe. Lastly, technological advancements continue to refine the methods used in both ground-based and space telescopes. Adaptive optic systems, crucial for correcting atmospheric distortion, have been integrated into the 30-meter telescope, TMT, enhancing its ability to observe faint objects with clarity approaching that of space telescopes. This improvement is vital for studying distant galaxies, star-forming regions, and the atmospheres of exoplanets, making it possible to detect subtle details that were previously beyond reach. As 2024 progresses, these advancements highlight humanity's expanding capacity to explore and understand the cosmos. From investigating the earliest structures in the universe to laying the groundwork for human exploration on Mars, the astronomical and technological achievements of this year are crucial steps toward uncovering the universe's mysteries. Each discovery not only enriches our scientific knowledge, but also paves the way for future missions that may redefine humanity's role as an explorer and observer of the cosmos, ensuring that the next era of astronomy will be one of unprecedented discovery and understanding. As we continue to explore the developments in astronomy throughout 2024, the field is marked by rapid advancements across various domains, from unraveling cosmic mysteries to expanding human space missions and refining our understanding of planetary environments. These efforts are not only pushing the boundaries of scientific knowledge, but also preparing the next generation of missions that could reshape humanity's place in the universe. A major focus has been on refining our understanding of how black holes form and evolve. The Event Horizon Telescope, EHT, has built upon its historic first image of a black hole by capturing detailed observations of Sagittarius A*, the supermassive black hole at the center of the Milky Way. These new images provide insights into the behavior of magnetic fields in the accretion disk surrounding the black hole, which are critical for understanding how material is funneled into the black hole and how powerful jets of energy are launched. These observations support the theory that magnetic fields play a key role in regulating the flow of matter and energy, influencing the growth and activity of black holes over time. Further studies into intermediate mass black holes, IMBHs, have also gained momentum. These black holes, believed to bridge the gap between stellar mass and supermassive black holes, have remained elusive. However, the James Webb Space Telescope, JWST, has detected the presence of several IMBHs within globular clusters by observing the orbits of stars influenced by these unseen massive objects. Understanding IMBHs is crucial for piecing together how supermassive black holes grow, as these intermediate forms may merge and coalesce over billions of years to form the enormous black holes that anchor galaxies. In cosmology, the study of cosmic inflation continues to advance. By analyzing data from the Planck satellite, the South Pole Telescope, SPT, and the Atacama Cosmology Telescope, ACT, researchers have refined models that describe the rapid expansion of the universe immediately following the Big Bang. This year's studies focus on the characteristics of the inflationary field, particularly its energy levels and particle interactions, to better understand how the universe's large-scale structure emerged. These insights are helping astronomers reconcile small discrepancies in the cosmic microwave background, CMB data with inflationary models, bringing us closer to a unified understanding of the universe's earliest moments. In addition, the Euclid mission has made strides in mapping the distribution of dark matter and dark energy. The mission's advanced imaging and spectroscopic capabilities are being used to create a 3D map of galaxies and cosmic structures, highlighting how dark matter clusters and how dark energy influences the expansion of the universe. Early results indicate that the universe's acceleration might be slightly different than previously thought, prompting a re-evaluation of dark energy's role and characteristics. Such findings are crucial for testing alternative theories of gravity and understanding the universe's long-term fate. On the search for extraterrestrial life, 2024 has seen major advancements in characterizing exoplanet atmospheres. The JWST has observed multiple planets within the habitable zones of their stars, identifying water vapor, carbon dioxide, and other key molecules that could indicate the presence of life-sustaining environments. One notable finding is the detection of potential biosignature gases on a super-Earth orbiting a nearby red dwarf star. Researchers are focusing on the ratios and chemical interactions of these gases, as the simultaneous presence of certain molecules, such as methane and oxygen, could suggest biological activity. The combination of these gases would usually react and neutralize each other, unless an ongoing process, potentially biological, replenishes them. Technological advancements are also enabling more precise studies of these distant worlds. The European Space Agency's Plato mission, specifically designed to find Earth-like exoplanets, is scanning thousands of stars, identifying planets that might have conditions similar to Earth's. By combining Plato's extensive data with the JWST's high-resolution atmospheric studies, astronomers are building a comprehensive catalog of exoplanets with the highest potential for habitability. This collaborative approach is refining the search for life beyond Earth, focusing resources on the most promising candidates. The technological frontier continues to expand with the development of the Extremely Large Telescope, ELT, and its adaptive optic systems. These innovations allow astronomers to overcome atmospheric distortion, providing ground-based observations with clarity comparable to space telescopes like the JWST. The ELT's capability to directly image exoplanets and study their atmospheres in unprecedented detail is expected to revolutionize the search for biosignatures and refine models of planet formation. Meanwhile, human space missions are moving towards more ambitious goals. The Artemis program is gearing up for the first crewed lunar landing in decades, with Artemis 3 targeting the moon's south pole. This mission will establish the foundations for a sustainable human presence, deploying habitats, life support systems, and infrastructure that will be critical for long-term operations. The success of Artemis 3 is vital as it sets the stage for Mars missions, testing technology and strategies needed for deep space exploration. The Lunar Gateway, an orbiting station around the moon, is also advancing as a crucial part of this strategy. This international effort, involving NASA, ESA, Roscosmos, and others, aims to provide a staging point for lunar and deep space missions. The Gateway will offer research facilities, docking stations for crewed and robotic missions, and laboratories for studying space weather, radiation, and life sciences. It represents a collaborative effort to extend humanity's reach beyond Earth's orbit and supports the long-term vision of exploring Mars and other distant planetary bodies. Mars exploration continues with the Perseverance rover, which is actively collecting samples in Jezero crater. The samples collected are being prepared for return to Earth through the Mars Sample Return Mission, an unprecedented international collaboration. These samples hold the potential to reveal signs of ancient microbial life, offering critical evidence about Mars's habitability billions of years ago. If life existed there, it would be the first direct proof of life beyond Earth, profoundly influencing the fields of astrobiology and planetary science. In the outer solar system, the Europa Clipper mission is being prepared to explore the subsurface ocean of Jupiter's moon Europa. Scheduled to launch in the late 2020s, this mission will analyze the composition of Europa's ice and water vapor plumes, searching for organic molecules that could indicate the presence of life. Coupled with ESA's JUICE mission, which targets both Europa and Ganymede, these efforts aim to uncover whether these icy worlds can support life. These missions build upon previous discoveries from Galileo and Cassini, enhancing our understanding of ocean worlds and their potential as habitable environments. The astronomical achievements of 2024 illustrate humanity's deepening ability to explore and understand the cosmos, from refining theories of cosmic evolution and inflation to searching for life across the galaxy and expanding human presence beyond Earth. Each discovery and technological advance lays the groundwork for future explorations, ensuring that the next chapter in space exploration will be one of unprecedented discovery and transformative understanding. As 2024 progresses, the scope of astronomical advancements and discoveries broadens further, encompassing deeper investigations into fundamental cosmological phenomena, the expansion of human space missions, and novel techniques for detecting extraterrestrial life. Each step forward is not only a testament to technological prowess, but also a critical step in unraveling the mysteries of the universe. One of the significant areas of focus remains the study of the universe's early structure and formation. The James Webb Space Telescope, JWST, has continued to observe galaxies forming within the first billion years after the Big Bang, providing critical insights into how these early structures coalesced. Recent data has shown that some of these galaxies grew faster and were more massive than previously expected, suggesting that star formation and galactic evolution occurred rapidly in the early Universe 7 Source 8 source. This challenges current models of cosmology and galaxy formation, prompting scientists to refine their theories to account for the availability of gas and the dynamics of dark matter that might have accelerated early cosmic growth. In addition to these early galaxies, the detection of population 3 stars, hypothetical first-generation stars composed almost entirely of hydrogen and helium, remains a crucial objective. The JWST has detected indirect signatures consistent with these stars in the halos of ancient galaxies. Such observations are vital, as they provide the first clues about the universe's transition from a simple state dominated by light elements to a complex structure filled with stars, galaxies, and heavier elements. Finding these first-generation stars helps explain the processes that initiated the chemical evolution necessary for planet formation and life. Dark matter and dark energy studies have also gained momentum. The European Space Agency's ESA Euclid mission has launched successfully and is now collecting high-resolution data to create a detailed map of dark matter distribution across the cosmos. By observing the gravitational lensing effects of dark matter, where the gravity of unseen mass bends light from distant galaxies, Euclid helps reveal how this mysterious substance clumps together and influences the large-scale structure of the universe. Initial data from Euclid has already begun refining models of dark matter behavior, showing that its distribution might be more intricate than previously thought. This new information is essential for understanding how galaxies form and evolve over billions of years. The role of dark energy, which drives the accelerated expansion of the universe, is also being explored through this mission. By mapping how galaxies are distributed and how light travels through space, Euclid's findings contribute to a better understanding of how dark energy shapes the universe's fate. These observations are critical for testing theories of gravity and exploring whether new physics beyond Einstein's general relativity might be needed to explain the universe's behavior. The collaboration between Euclid and ground-based telescopes, such as the Dark Energy Spectroscopic Instrument, DESI, has further enhanced these studies. By combining their datasets, astronomers have constructed more accurate 3D maps of galaxy distribution, tracing the cosmic web's filaments and voids with unprecedented precision. These maps help refine our knowledge of how the universe's expansion and the distribution of dark matter and dark energy work in tandem. In the realm of exoplanet exploration, the JWST has been instrumental in studying planets within habitable zones, regions around stars where liquid water could exist. This year, it detected water vapor in the atmospheres of several exoplanets orbiting red dwarf stars, some of the most common types of stars in our galaxy. Such findings increase the probability of discovering planets with conditions suitable for life, as red dwarfs often host multiple rocky planets within their habitable zones. The detection of complex molecules, such as methane and carbon dioxide, alongside water vapor in these planets' atmospheres raises intriguing possibilities regarding the presence of life-supporting environments. Alongside JWST, the European Space Agency's Plato mission is broadening the hunt for Earth-like exoplanets. By observing thousands of stars and their transits, Plato is expected to discover planets that are not only in habitable zones, but also have Earth-like sizes and compositions. The combination of Plato's broad survey capabilities with the detailed atmospheric analysis of the JWST forms a powerful partnership, enabling astronomers to prioritize the most promising candidates for life. Technological advancements in telescope capabilities have also reached new heights with the development of the extremely large telescope, YELT. The YELT's 39-meter mirror is designed to capture light with unprecedented resolution, allowing direct imaging of exoplanets and detailed study of their atmospheres. The integration of adaptive optic systems within the YELT corrects for Earth's atmospheric distortion, making ground-based observations as precise as those of space-based telescopes. This advancement is critical for detecting biosignatures, such as oxygen or other life-indicating molecules, in the atmospheres of distant planets, potentially offering the first evidence of extraterrestrial life. Meanwhile, human space exploration continues its push beyond Earth. NASA's Artemis program, in collaboration with international partners, is progressing towards the Artemis 3 mission, which aims for a crewed landing on the Moon's south pole. This mission will establish a foundation for sustainable lunar exploration, deploying habitats, energy systems, and research facilities designed for long-term habitation. Artemis 3 is crucial for testing the technologies needed for future Mars missions, such as life support systems and resource utilization technologies like extracting water from lunar regolith. The Lunar Gateway, a multi-agency initiative involving NASA, ESA, and other space agencies, is set to support these efforts by orbiting the Moon and acting as a hub for lunar missions and future deep space exploration. The Gateway's laboratories will facilitate research on microgravity's effects on biology and technology, as well as testing advanced propulsion systems and radiation shielding, which are critical for missions to Mars and beyond. Mars remains a focal point for exploration, with the Mars Sample Return mission moving forward. The Perseverance rover has been diligently collecting rock and soil samples from Mars' Jezero crater, an ancient lakebed thought to have had the right conditions for microbial life billions of years ago. These samples, set to be returned to Earth through an international collaboration between NASA and ESA, are expected to provide the most definitive evidence yet of Mars' past habitability. In the outer solar system, interest in exploring icy moons continues to grow. The upcoming Europa Clipper mission is on track to investigate the subsurface ocean of Jupiter's moon Europa, analyzing its ice crust and water plumes for organic molecules and chemical signatures indicative of life. The Clipper's flybys aim to confirm whether the conditions beneath Europa's ice could support microbial ecosystems similar to those found near Earth's deep-sea hydrothermal vents. Coupled with ESA's JUICE mission, which will explore Europa and other Jovian moons like Ganymede, these missions are designed to gather crucial data about the potential for life beyond Earth. The search for intelligent extraterrestrial civilizations has also expanded with the Square Kilometre Array, SK, and other advanced radio observatories. SK's wide-ranging capabilities allow for the detection of faint radio signals across vast swathes of the galaxy, significantly increasing the chances of discovering technosignatures, signals that might indicate the presence of advanced civilizations. If detected, such signals would not only revolutionize our understanding of life in the universe, but also spark a profound shift in how humanity views its place in the cosmos. The astronomical advancements of 2024 exemplify humanity's increasing ability to explore and understand the universe on multiple fronts, from the detailed study of early galaxies and the cosmic web to the expanding efforts in human space missions and the refined search for habitable worlds. Each discovery and technological leap paves the way for future explorations that promise to deepen our knowledge of cosmic evolution, the potential for life beyond Earth, and our capacity for long-term space habitation. As 2024 unfolds, the advances in astronomy continue to illuminate new frontiers, pushing deeper into the mysteries of cosmic evolution, planetary science, and technological breakthroughs that support the expansion of human exploration beyond Earth. Each discovery not only enriches our understanding of the universe, but also sets the stage for even more ambitious missions and studies. A focal point of 2024 has been the study of early cosmic phenomena, particularly the processes that shaped the first stars and galaxies. The James Webb Space Telescope, JWST, remains at the forefront, detecting ancient galaxies that formed just a few 100 million years after the Big Bang. Recent observations have identified galaxy protoclusters, groups of galaxies forming close together, that challenge existing models of galaxy formation. These early structures appear to have undergone rapid star formation, producing heavy elements much sooner than anticipated. This discovery suggests that the first stars, often referred to as population 3 stars, might have ignited the chemical processes necessary for the evolution of galaxies sooner than predicted. Dark matter studies are also taking a significant leap forward this year. The Euclid mission, launched by the European Space Agency, is mapping dark matter with high precision through gravitational lensing effects. By observing how light from distant objects bends as it passes through dark matter, Euclid provides a clearer view of the distribution and behavior of this elusive substance. Early findings show that dark matter clusters in ways that differ slightly from previous simulations, hinting that our understanding of its properties might need refining. These results are crucial for understanding the role dark matter plays in galaxy formation and the overall structure of the universe. The synergy between Euclid's space-based observations and the ground-based dark energy spectroscopic instrument, DESI, enhances this work. Together, these instruments offer a comprehensive look at how dark energy, which drives the universe's expansion, interacts with dark matter and influences galaxy formation. The data gathered is helping astronomers refine models that describe how the universe evolved and predict its ultimate fate. In exoplanet research, the JWST has been instrumental in detecting and analyzing atmospheres of planets within their stars' habitable zones. One of the year's key findings involves a super-Earth located in the habitable zone of a red dwarf star, where JWST identified signatures of water vapor and carbon-based molecules. Such detections are critical because they suggest the possibility of life-supporting environments beyond our solar system. The combination of these findings with upcoming observations from missions like the European Space Agency's Plato will allow scientists to build a robust catalog of exoplanets that might host life. Moreover, the integration of JWST and Plato's capabilities enables a more strategic approach in exoplanet studies. While Plato focuses on finding Earth-like planets by monitoring their transits across stars, JWST delves deeper into their atmospheric compositions. This collaboration accelerates the search for biosignatures, compounds like methane, oxygen, or carbon dioxide that could hint at biological activity, by narrowing down the list of promising candidates for detailed analysis. The technological frontier is also advancing rapidly. The extremely large telescope, YELT, with its 39-meter aperture, is now operational, providing the sharpest ground-based observations ever achieved. Its adaptive optics systems allow astronomers to study faint, distant objects with clarity approaching that of space-based observatories. The YELT's capabilities include directly imaging exoplanets and studying their atmospheres for signs of life, making it a critical tool in the ongoing search for habitable worlds. Observations made by the YELT are expected to complement JWST's work, offering detailed images and data on protoplanetary disks, the regions where planets form, helping scientists refine models of planet formation and evolution. Meanwhile, human space exploration is making significant strides, particularly through NASA's Artemis program. Artemis 3 is scheduled to land astronauts on the Moon's south pole, establishing the first long-term lunar base. This mission will test new technologies such as lunar habitats, sustainable power systems, and in-situ resource utilization techniques like extracting water from lunar ice to support future missions. The success of Artemis 3 is vital as it lays the groundwork for human missions to Mars, testing life support and propulsion systems necessary for deep space travel. The Lunar Gateway Project, a collaboration among NASA, ESA, Roscosmos, and other international agencies, is set to play a crucial role in supporting these missions. By orbiting the Moon, the Gateway will serve as a hub for scientific research, crewed missions, and even lunar and Mars-bound spacecraft. Its laboratories will facilitate studies on space weather, the effects of radiation on biological systems, and advanced technologies needed for long-term space habitation. The Gateway's development underscores a significant step forward in international cooperation and in expanding human activities beyond low Earth orbit. Mars remains a focal point for exploration. The Mars Sample Return Mission, an international collaboration between NASA and ESA, is moving forward with Perseverance continuing its work in Jezero Crater. The samples collected are expected to provide the most definitive evidence yet of ancient life on Mars, with scientists preparing for their analysis on Earth. If microbial life or signs of past habitability are confirmed, it would mark a historic milestone in astrobiology. Beyond Mars, the exploration of icy moons such as Europa and Enceladus is advancing. The Europa Clipper mission, set to launch later this decade, is designed to explore the potential habitability of Europa's subsurface ocean. By flying through the moon's water vapor plumes, the Clipper will collect and analyze samples for organic compounds and chemical signatures of hydrothermal activity. This mission builds on previous findings from Galileo and Cassini, which suggested that these moons could harbor environments similar to Earth's deep-sea hydrothermal vents, where life thrives in the absence of sunlight. Technological advancements are also enhancing the search for intelligent extraterrestrial civilizations. The Square Kilometre Array, SK, currently the most sensitive radio telescope array ever built, is scanning the skies for technosignatures, signals that could indicate the presence of advanced alien technologies. SK's ability to monitor vast areas of the sky across multiple frequencies simultaneously increases the chances of detecting unusual signals, making it a key instrument in the search for life beyond Earth. Such a discovery would fundamentally alter our understanding of life in the universe, prompting a new era of exploration and research. In addition to these astronomical and technological achievements, the study of cosmic phenomena, such as gravitational waves, has continued to evolve. The LIGO-Virgo-Cagra network, now operating with enhanced sensitivity, has detected several events involving binary mergers of black holes and neutron stars. These detections provide invaluable insights into the most extreme environments in the universe, testing the limits of general relativity and offering clues about how heavy elements like gold are formed during these cataclysmic collisions. Looking ahead, humanity's ambitions in space are growing, with plans for lunar bases, Martian missions, and beyond. The next generation of telescopes and space missions is poised to further refine our understanding of the universe's origins, the nature of dark matter and dark energy, and the potential for life on distant worlds. Each technological leap, from adaptive optics to advanced space observatories, not only expands our capacity to observe the cosmos, but also prepares the ground for transformative discoveries that could redefine humanity's role in the vast, interconnected universe. As 2024 progresses, the landscape of astronomical research continues to expand with groundbreaking discoveries and advancements in technology, deepening our understanding of cosmic evolution, planetary systems, and the potential for extraterrestrial life. This period has been marked by both innovative missions and collaborations that are pushing the boundaries of what is possible in space exploration and observation. A central focus remains the exploration of the earliest galaxies in the universe. The James Webb Space Telescope, JWST, has been instrumental in observing galaxies from the first few hundred million years after the Big Bang. These observations have revealed that early galaxies were not only forming stars at a rapid rate, but also growing into massive structures faster than previously expected. The data shows an abundance of heavy elements in these galaxies, suggesting that star formation and supernova explosions occurred early on, enriching the interstellar medium and accelerating galactic evolution. This challenges and refines existing models of cosmology, highlighting the need for new simulations to account for such rapid early growth. The detection of population 3 stars remains a key objective. JWST has provided indirect evidence of these primordial stars, which are thought to be the universe's first stars, composed almost entirely of hydrogen and helium. These stars are crucial for understanding the chemical evolution that set the stage for later star and planet formation. If JWST can confirm the presence of population 3 stars by observing their spectral signatures, it would be a monumental step in tracing the universe's evolution from simplicity to complexity. Meanwhile, the study of dark matter and dark energy continues to be at the forefront of cosmological research. The Euclid mission, launched by ESA, is using gravitational lensing techniques to map the distribution of dark matter on a cosmic scale. By observing how light from distant galaxies bends as it passes through regions dense with dark matter, Euclid has begun constructing the most detailed 3D map of dark matter ever created. Early findings indicate that the behavior of dark matter might deviate slightly from predictions based on previous models, prompting astronomers to reconsider aspects of dark matter's role in galaxy formation. Dark energy, the force responsible for the accelerated expansion of the universe, is also under investigation. Euclid's data, combined with observations from the Dark Energy Spectroscopic Instrument DESI, provides insights into how dark energy influences the expansion of the universe over billions of years. These combined datasets are crucial for testing theories about the nature of dark energy, such as whether it is a constant force or if it evolves over time. Understanding this could fundamentally change our view of the cosmos and its ultimate fate. The search for habitable exoplanets and potential biosignatures has accelerated, with the JWST playing a critical role. This year, JWST has identified water vapor and organic molecules in the atmospheres of several exoplanets orbiting within the habitable zones of their stars. Such findings increase the potential for discovering planets that could support life, particularly those orbiting red dwarf stars, which are abundant and often host multiple rocky planets at source. By targeting planets with detectable water vapor and atmospheric components like methane and carbon dioxide, astronomers are refining their methods to search for signs of life beyond Earth. Additionally, the Plato mission by ESA complements JWST's efforts by focusing on the detection of Earth-like planets through transit observations. Plato's broad observational range allows it to identify planets that pass in front of their stars, enabling detailed follow-up studies with JWST to characterize their atmospheres. This combined effort enhances the likelihood of finding exoplanets with conditions conducive to life, making the search for extraterrestrial biosignatures more precise and focused. The technological advancements seen in 2024 also include the operational readiness of the Extremely Large Telescope, YELT. With its massive 39-meter mirror, the YELT is now the most powerful ground-based observatory, capable of direct imaging of exoplanets and their atmospheres. The YELT's adaptive optics system, which counteracts atmospheric distortion, allows it to study faint and distant objects with the clarity of a space telescope. These capabilities are crucial for detecting biosignatures in exoplanetary atmospheres and for investigating the environments where new planets are forming, giving astronomers unprecedented insight into planetary and star formation processes. The human aspect of space exploration is also making significant strides. NASA's Artemis program is progressing towards the Artemis 3 mission, which will see astronauts land on the Moon's South Pole. This mission aims to establish the first long-term lunar base, designed to support extended human operations by testing technologies such as habitat construction, life support systems, and in-situ resource utilization, ISRU, techniques like extracting water from lunar ice. Artemis 3 is not just about returning to the Moon. It serves as a crucial step towards Mars, preparing technology and strategies for long-duration missions beyond Earth. The Lunar Gateway, an international space station orbiting the Moon, is an integral part of this vision. Developed in collaboration with international partners such as ESA, Roscosmos, and others, the Gateway will support lunar missions and future expeditions to Mars. Its laboratories will facilitate research on the effects of microgravity and space radiation on human biology, as well as test advanced propulsion systems necessary for interplanetary travel. This development marks a critical milestone in extending human presence beyond low Earth orbit and establishing a sustainable infrastructure for exploring deeper into the solar system. Mars exploration remains a centerpiece of these efforts. The Mars Sample Return Mission, a collaboration between NASA and ESA, is advancing with the Perseverance rover's ongoing collection of rock and soil samples from Jezero crater. These samples, set to be returned to Earth by the end of the decade, are expected to provide unprecedented insights into Mars's past habitability. If the samples reveal ancient microbial life or conditions that could have supported life, it would represent a historic breakthrough in astrobiology, proving that Earth is not the only planet capable of hosting life. Exploration efforts are also extending to the icy moons of the outer solar system. NASA's Europa Clipper mission is scheduled to launch later this decade to study the subsurface ocean of Jupiter's moon Europa. By flying through water vapor plumes that erupt from the moon's ice shell, the Clipper aims to detect organic molecules and other signs of hydrothermal activity, which could indicate the potential for life. This mission, coupled with ESA's JUICE mission targeting Ganymede and Europa, aims to determine whether these moons possess the necessary conditions for life and to gather data that could inform future missions, including potential landers. The search for intelligent extraterrestrial civilizations is being revitalized with the Square Kilometer Array, SKA. This powerful radio telescope array has the capability to monitor enormous portions of the sky, scanning for technosignatures, artificial signals that might indicate advanced civilizations. With its ability to observe across a wide range of frequencies and cover vast areas simultaneously, SKA significantly increases the chances of detecting such signals, making it the most comprehensive attempt yet to answer the age-old question: are we alone in the universe? Lastly, the study of gravitational waves continues to evolve, with the LIGO-Virgo-Cagra network detecting multiple events involving neutron star and black hole mergers. These detections offer crucial insights into the extreme physics of the universe, helping astronomers understand how heavy elements are created and testing the limits of general relativity under extreme conditions. Such studies not only enhance our understanding of the universe's most energetic events, but also open new avenues for observing the cosmos in ways beyond traditional light-based methods. As 2024 continues, each technological and observational advancement contributes to a deeper and more interconnected understanding of the universe. From the development of sustainable lunar bases and the expansion of Mars missions to the search for life on distant exoplanets and the mapping of dark matter and dark energy, the astronomical efforts of this year are laying the groundwork for future discoveries that will redefine humanity's understanding of its place in the cosmos. As we proceed through 2024, the frontiers of astronomy and space exploration continue to expand, offering new insights into cosmic phenomena, enhancing human spaceflight capabilities, and deepening the quest for extraterrestrial life. The discoveries and technological advancements this year have been crucial in shaping our understanding of both our solar system and the universe beyond. One of the most significant focuses of 2024 has been the detailed study of gravitational waves and their implications for understanding the universe's most extreme events. The LIGO-Virgo-Cagra collaboration has upgraded its detectors, leading to higher sensitivity and a more comprehensive dataset of black hole and neutron star mergers. These observations have detected several new events that provide critical insights into how such massive collisions produce gravitational waves and how these phenomena contribute to the formation of heavy elements like gold and platinum. The detection of such events not only validates the predictions of general relativity under extreme conditions, but also allows astronomers to explore the environments surrounding these mergers. Some recent findings indicate that mergers occurring within dense stellar environments, such as globular clusters, produce distinctive gravitational wave signatures, which could help refine our understanding of how these stellar objects interact and evolve over time. The James Webb Space Telescope, JWST, remains a crucial tool for exploring the early universe, providing a clearer picture of galaxy formation and evolution. In 2024, JWST captured high-resolution images of ancient galaxies and protoclusters, shedding light on the processes that shaped the universe during its first billion years. These observations have confirmed that galaxies formed and grew more rapidly than previously modeled, with high rates of star formation and supernova activity enriching the cosmos with heavy elements at an accelerated pace. Furthermore, the telescope's ability to detect infrared light has allowed astronomers to study the chemical signatures of these early galaxies, providing direct evidence of the presence of elements like carbon and oxygen, key ingredients for life as we know it. These findings refine models of the early universe and offer new pathways for understanding how galaxies like the Milky Way evolved. Dark matter and dark energy remain critical areas of research, especially with the ongoing observations from the Euclid mission. By mapping dark matter through gravitational lensing, where the gravity of unseen mass bends light from distant galaxies, Euclid has produced high-precision 3D maps that reveal the distribution and behavior of dark matter on a cosmic scale. Early results suggest that dark matter may be more dynamically distributed than current models account for, prompting revisions to theories of galaxy formation. Euclid's efforts are complemented by ground-based observatories, such as the Dark Energy Spectroscopic Instrument, DESI. Together, these observatories provide a comprehensive view of how dark matter clusters influence the formation and expansion of the universe. The integration of these datasets is also critical for studying dark energy and testing alternative models of gravity that might better explain the accelerated expansion of the universe. On the frontier of exoplanet research, JWST and the European Space Agency's Plato mission are working in tandem to identify and characterize Earth-like planets. Plato's transit observations are particularly effective at discovering planets that orbit within their star's habitable zones, where conditions might be suitable for liquid water. JWST follows up on these findings, analyzing planetary atmospheres for signs of water vapor, carbon dioxide, and other biosignature gases. These joint efforts have led to the discovery of several promising candidates this year, making the search for habitable environments beyond Earth more focused and data-driven. The technological advances in adaptive optics, particularly in the newly operational Extremely Large Telescope, YELT, are further enhancing our ability to observe and study exoplanets directly. The YELT's powerful 39-meter mirror, combined with sophisticated adaptive optic systems, allows it to observe faint objects with a clarity that rivals space telescopes. This capability is crucial for directly imaging exoplanets, studying their atmospheres, and detecting potential biosignatures like oxygen and methane, key indicators that could suggest the presence of life. Human space exploration continues to accelerate, with NASA's Artemis program making significant progress. Artemis 3, scheduled for launch this year, will aim to land astronauts on the Moon's South Pole, a region rich in water ice that could be used for sustaining long-term lunar habitats. This mission will deploy new technologies for in-situ resource utilization, including systems designed to extract and process lunar ice into breathable oxygen and rocket fuel, crucial for supporting extended missions and future Mars expeditions. In tandem with Artemis, the development of the Lunar Gateway is advancing. This collaborative international project, involving NASA, ESA, Roscosmos, and other space agencies, is designed to support long-term lunar missions and serve as a staging point for deep space exploration. The Gateway will offer laboratory facilities for research on radiation shielding, life support systems, and advanced propulsion technologies, preparing for the eventual human missions to Mars. Its modular design allows for continuous expansion and adaptation, ensuring it remains a vital hub for international cooperation in space. The Mars Sample Return Mission, an ongoing collaboration between NASA and ESA, also progresses as the Perseverance rover continues its exploration of Jezero Crater. The rover's work in collecting and storing rock and soil samples aims to uncover definitive signs of past life on Mars. These samples, once returned to Earth, could provide the clearest evidence yet of microbial life beyond Earth, offering unprecedented insights into the planet's geological and biological history. The exploration of icy moons in the outer solar system is gaining momentum as well. The Europa Clipper mission is set to investigate Jupiter's moon Europa, a prime candidate for extraterrestrial life due to its subsurface ocean. By flying through plumes of water vapor emerging from beneath Europa's ice crust, the Clipper will collect data on the moon's potential habitability. The mission's findings could confirm the existence of organic compounds and chemical interactions similar to those found in Earth's deep-sea hydrothermal vents, where life thrives without sunlight. The search for intelligent life has expanded with the capabilities of the Square Kilometer Array, SKA. This radio telescope array is the most sensitive ever built, and it continues to monitor the galaxy for technosignatures, artificial signals that could indicate advanced civilizations. Its ability to cover vast areas of the sky and analyze a wide spectrum of frequencies simultaneously makes it the most powerful tool in the ongoing search for extraterrestrial intelligence. If SK detects any techno-signatures, it would mark one of the most significant discoveries in human history, fundamentally shifting humanity's understanding of its place in the cosmos. Finally, the study of gravitational waves is transforming how we observe and understand the universe. The LIGO-Virgo-Cagra network has achieved breakthroughs in detecting waves from black hole mergers and neutron star collisions. These events provide crucial data about the universe's structure and evolution, offering insights into the formation of heavy elements and testing the boundaries of current physical models. The continued refinement of these detectors promises even more detailed observations, potentially uncovering new types of astrophysical events. The astronomical advancements of 2024 highlight humanity's increasing ability to explore and understand the universe across multiple domains. From detailed studies of the early cosmos and dark matter to expanding human presence on the moon and the search for life on distant planets, each discovery and technological leap lays the foundation for future explorations that promise to transform our understanding of the universe and our place within it. As 2024 unfolds further, the field of astronomy continues to witness transformative developments across various domains, from cosmic observation to planetary science and the advancement of human space exploration. These efforts are unlocking new chapters in our understanding of the universe, building the foundation for future discoveries, and expanding the horizons of human presence beyond Earth. A critical area of research this year has been the observation of the earliest galaxies and cosmic structures using the James Webb Space Telescope, JWST. JWST's infrared capabilities have enabled astronomers to look deeper into the early universe, observing galaxies that formed as early as a few 100 million years post-Big Bang. These galaxies reveal unexpectedly high levels of star formation, suggesting that the conditions in the early universe were highly conducive to rapid development. This finding challenges traditional models of galaxy formation, which assumed a slower evolution due to limited availability of heavy elements at that time. Furthermore, JWST has provided key insights into the presence of heavy elements, such as carbon and oxygen, within these early galaxies, indicating that supernovae were actively enriching the interstellar medium much earlier than anticipated. This supports the hypothesis that population 3 stars, massive, short-lived stars thought to be the first generation after the Big Bang, played a crucial role in seeding the universe with these elements. Confirming the existence and behavior of these early stars is essential for understanding how subsequent generations of stars and galaxies, including our own Milky Way, came to be. Simultaneously, dark matter and dark energy studies are evolving rapidly. The Euclid mission's high-resolution mapping of dark matter via gravitational lensing is providing unprecedented detail about how this invisible substance is distributed throughout the cosmos. Early findings from Euclid suggest that dark matter may interact with itself or other forms of matter differently than previously believed, requiring updates to current models. The insights from these observations are also refining our understanding of how dark matter influences the structure and evolution of galaxies. Additionally, the combined efforts of the Dark Energy Spectroscopic Instrument, DESI, and Euclid are generating a comprehensive dataset on how dark energy affects the universe's expansion. These instruments allow astronomers to study the expansion rate across different cosmic epochs, offering clues about whether dark energy is a constant force or if it evolves over time. Such information is crucial for determining the universe's long-term fate, whether it will continue expanding indefinitely, slow down, or eventually collapse. In planetary science, the search for habitable exoplanets and potential biosignatures has seen major advancements. The JWST has successfully identified atmospheres containing water vapor and organic molecules in several exoplanets located within the habitable zones of their stars. Such discoveries are vital as they suggest that these planets could have conditions similar to Earth's, increasing the likelihood of finding environments that support life. These findings are part of a broader collaborative effort, with ESA's Plato mission focusing on detecting Earth-like planets through precise transit observations, while JWST follows up with detailed spectroscopic analysis. The synergy between these missions is crucial, as it enables a more targeted search for biosignatures, chemical compounds like methane, carbon dioxide, and oxygen that may indicate biological activity. If these compounds are found together in specific ratios, they could signal the presence of life, as these gases typically interact and cancel each other out unless replenished by biological processes. Such detailed analyses are becoming increasingly feasible with the technology and methods employed by current and upcoming missions. Meanwhile, ground-based observatories like the extremely large telescope YELT have become instrumental in advancing these studies. The YELT's massive aperture and state-of-the-art adaptive optic systems allow for direct imaging of exoplanets and detailed atmospheric characterization. This capability is crucial for confirming biosignatures and understanding the conditions that shape planetary atmospheres, helping to pinpoint where life might exist beyond our solar system. Human space exploration is another rapidly advancing frontier in 2024. NASA's Artemis program is moving forward with Artemis 3, aiming to land astronauts on the Moon's South Pole, a region believed to contain significant water ice deposits. The mission will test new technologies for long-term lunar habitation, including systems for extracting and utilizing lunar resources to produce water, oxygen, and fuel. These developments are essential for establishing a sustainable human presence on the Moon, which will serve as a stepping stone for future crewed missions to Mars. The Lunar Gateway, a multinational space station in lunar orbit, continues to develop as a critical component of this strategy. The Gateway will provide research facilities for studying the effects of long-term exposure to space radiation, microgravity, and the logistics of deep space travel. It will also serve as a hub for future lunar missions, acting as a relay point for spacecraft traveling between Earth, the Moon, and eventually Mars. This collaboration between NASA, ESA, Roscosmos, and other international partners exemplifies the increasing cooperation needed for humanity's expansion beyond Earth's orbit. Mars remains a priority, with the Mars Sample Return mission progressing. The Perseverance rover is actively gathering and storing samples from Mars' Jezero crater, an ancient lakebed that might have once hosted microbial life. The samples, once returned to Earth, are expected to provide definitive evidence of whether life ever existed on Mars. This mission, a joint effort between NASA and ESA, is critical for understanding Mars's potential as a habitat and for preparing for future human exploration of the Red Planet. Beyond Mars, the search for life extends to the icy moons of the outer solar system. NASA's Europa Clipper mission is preparing to launch later this decade, targeting the subsurface ocean of Jupiter's moon Europa. This mission will analyze plumes of water vapor erupting from beneath Europa's ice shell, searching for organic compounds and chemical signs of hydrothermal activity, key indicators of habitability. The mission builds on earlier discoveries from the Galileo and Cassini spacecraft, reinforcing the idea that ocean worlds could be the most promising locations for finding life beyond Earth. The quest for intelligent extraterrestrial civilizations also continues, with the Square Kilometre Array, SK, playing a central role. This powerful radio telescope array has begun its extensive survey of the sky, scanning for technosignatures, signals that could indicate the presence of advanced civilizations. SK's unprecedented sensitivity and ability to monitor vast portions of the sky make it the most comprehensive search for extraterrestrial intelligence to date. If successful, the detection of such signals would not only transform our understanding of life in the universe, but also fundamentally alter humanity's perspective on its place within it. Finally, the study of gravitational waves has continued to evolve, providing insights into the most energetic events in the universe. The upgraded LIGO-Virgo-Cagra network has captured several new types of wave events, including neutron-star mergers that produce heavy elements. These detections offer direct evidence of how such elements are formed, adding another layer to our understanding of cosmic evolution. The data also test the predictions of general relativity under extreme conditions, offering new ways to probe the fundamental laws of physics. The discoveries and technological advancements of 2024 illustrate humanity's expanding reach into the cosmos. From early universe observations and exoplanet exploration to the development of sustainable lunar bases and Mars missions, each step taken this year lays the groundwork for a future where humanity could thrive beyond Earth. The continued integration of space missions, international collaborations, and cutting-edge technology ensures that the next era of space exploration will be one of unprecedented discovery and transformation. As we advance through 2024, the scope of astronomical exploration continues to broaden, with each new discovery offering critical insights into the cosmos and our place within it. From exploring the mechanics of black holes to developing the technology necessary for long-term human habitation beyond Earth, this year has been marked by profound advancements and international collaboration. One of the most significant breakthroughs has been in understanding the nature of black holes, particularly with data collected by the Event Horizon Telescope, EHT. Following its historic image of the black hole at the center of the M87 galaxy, the EHT has now focused on Sagittarius A*, the supermassive black hole at the center of our Milky Way. New observations provide more detailed images, highlighting the dynamics of its accretion disk and the magnetic fields shaping its environment. These studies confirm that magnetic fields play a pivotal role in regulating the flow of matter into black holes, influencing the jets of particles and energy they emit. The discovery and study of intermediate mass black holes, IMBHs, have also seen considerable progress. Using the capabilities of the James Webb Space Telescope, JWST, and data from ground-based observatories, astronomers have identified candidates for IMBHs within globular clusters. These findings are critical as IMBHs are believed to be the building blocks of supermassive black holes found in galaxy centers. Understanding their formation and growth processes provides insight into the evolutionary pathways that shaped the universe's largest structures. Simultaneously, studies into the universe's origins and evolution continue through cosmic background radiation analysis. The Planck satellite's detailed maps of the cosmic microwave background, CMB, combined with new measurements from the South Pole Telescope, SPT, and Atacama Cosmology Telescope, ACT, have allowed researchers to refine inflation models. By examining subtle fluctuations in the CMB, scientists are closing in on the specific properties of the inflationary period that expanded the universe, offering clearer insights into the conditions that prevailed shortly after the Big Bang. Another focal point of 2024 has been the mapping of the cosmic web, the vast network of galaxies, gas, and dark matter that forms the large-scale structure of the universe. The Euclid mission and the Dark Energy Spectroscopic Instrument DESI are leading this charge. Their combined efforts have provided the most detailed 3D map of the cosmic web, showing the distribution and behavior of dark matter. This map is crucial for understanding how galaxies form along these filaments and how dark energy influences the expansion of the universe. Early data from these missions indicate that some regions expand faster than others, prompting new hypotheses about the nature of dark energy. In exoplanet research, the synergy between the JWST and ESA's Plato mission has made significant strides in detecting and characterizing Earth-like planets. Plato has been identifying planets through transit observations, where a planet passes in front of its host star, causing a temporary dimming of light. JWST follows up by analyzing these planets' atmospheres, detecting components such as water vapor, carbon dioxide, and other potential biosignatures. Recent findings show several planets in the habitable zones of their stars with atmospheric compositions that raise the possibility of life-supporting environments. The ongoing development of the Extremely Large Telescope, YLT, enhances these studies by providing high-resolution, direct imaging of exoplanets and their atmospheres. Its capabilities, coupled with adaptive optics, allow it to observe atmospheric compositions with unprecedented precision. This technology is pivotal for detecting biosignatures like oxygen and methane in exoplanetary atmospheres, advancing the search for extraterrestrial life. Human space exploration has also been a major focus in 2024. NASA's Artemis 3 mission is set to land astronauts on the Moon's South Pole, where water ice deposits could support long-term human habitation. This mission will test new technologies for extracting and utilizing lunar resources, such as producing oxygen and fuel from lunar regolith. These advancements are critical for developing sustainable bases on the Moon, which will act as testing grounds for future Mars missions. The Lunar Gateway, an international collaborative effort, plays a key role in supporting these lunar missions. By providing a platform for scientific research and serving as a logistics hub for lunar operations, the Gateway will enable deeper exploration of the Moon and act as a stepping stone for Mars exploration. It will also facilitate studies on the effects of long-duration space travel, radiation shielding, and advanced propulsion systems, essential for deep space missions. Mars remains a priority, with the Mars Sample Return mission advancing through the efforts of NASA and ESA. The Perseverance rover continues to collect and store Martian rock samples, with the goal of returning them to Earth for analysis. These samples could provide definitive evidence of ancient microbial life on Mars, representing a groundbreaking moment in astrobiology if confirmed. Exploration of the icy moons of the outer solar system is also progressing, with NASA's Europa Clipper mission preparing for its upcoming launch. The Clipper aims to explore Europa's subsurface ocean by flying through its water vapor plumes, analyzing the composition for organic molecules and signs of hydrothermal activity. These findings could confirm whether Europa has the necessary conditions to support life, reinforcing the idea that ocean worlds beyond Earth might be habitable. The search for intelligent life continues with the Square Kilometre Array, SK, the most advanced radio telescope array ever built. Its ability to monitor the sky across a wide spectrum of frequencies makes it an unparalleled tool in the hunt for technosignatures, artificial signals that could indicate the presence of advanced civilizations. The SK's extensive reach and sensitivity increase the chances of detecting these signals, making it a critical instrument in the ongoing effort to answer whether humanity is alone in the universe. Lastly, the field of gravitational wave astronomy is evolving as the LIGO-Virgo-Chagrin network continues to detect and analyze wave events from the collisions of massive cosmic objects. These detections provide valuable insights into the nature of neutron star and black hole mergers, including how such events influence the distribution of elements throughout the universe. Observations are helping to refine models of how these violent events shape cosmic evolution and test the boundaries of general relativity in extreme conditions. The discoveries and technological advancements of 2024 represent a transformative era in astronomy and space exploration. From exploring the origins of the universe and mapping dark matter to preparing for lunar and Mars missions and seeking life beyond Earth, each development lays the groundwork for a new chapter of discovery. The continued international collaboration and integration of advanced technologies ensure that the future of space exploration will be more comprehensive, precise, and revealing than ever before. As 2024 progresses, the frontiers of astronomy and space exploration are expanding, marked by significant breakthroughs that deepen our understanding of cosmic structures, planetary systems, and the technology needed for human expansion beyond Earth. The achievements this year are setting the foundation for future discoveries and opening new pathways for international collaboration in space. One of the central achievements has been further insights into the nature of dark matter and dark energy, driven by the Euclid mission and the Dark Energy Spectroscopic Instrument DESI. By mapping the distribution of dark matter through gravitational lensing, Euclid has produced the most precise 3D models of the universe's large-scale structure to date. This work is critical because it shows how dark matter clusters influence galaxy formation and the expansion rate of the universe. Early data has indicated that the clustering patterns of dark matter might differ slightly from previous models, suggesting that our understanding of this mysterious substance requires updates. DESI, on the other hand, has been instrumental in studying how dark energy influences the cosmic web structure and the expansion rate of the universe. Combined with Euclid's findings, this research is refining models of cosmic expansion, providing crucial data for understanding whether dark energy is a constant force or evolves over time. This collaboration between space and ground-based observatories is vital for solving one of astronomy's most profound questions: the fate of the universe. Another key area of development has been the detailed study of black holes, especially through observations by the Event Horizon Telescope, EHT, and the James Webb Space Telescope, JWST. The EHT's latest observations of Sagittarius A*, the supermassive black hole at the center of our Milky Way, have provided more precise images of its accretion disk and the surrounding magnetic fields. These findings confirm that magnetic fields are instrumental in regulating the flow of matter into black holes and in shaping the jets that these massive objects emit. Such data is essential for refining our models of black hole growth and activity. JWST has also contributed significantly to the study of intermediate mass black holes, IMBHs. By observing globular clusters where these IMBHs are thought to reside, JWST has detected the influence of these hidden objects on surrounding stars, providing crucial evidence of their presence. These observations help explain how supermassive black holes might form from the merging of smaller black holes over time, offering insights into the growth of the universe's largest and most powerful structures. Cosmic evolution studies have been another major focus, particularly regarding the early universe. JWST's deep field observations have unveiled galaxies and protoclusters forming within the first billion years after the Big Bang. These early structures demonstrate unexpectedly rapid star formation rates and high levels of heavy elements, suggesting that the early universe was much more active and complex than previously thought. This challenges existing models, pushing scientists to revisit theories about the availability of gas and the impact of early supernovae on galaxy growth. Simultaneously, research into the cosmic microwave background, CMB, has advanced with data from the Planck satellite and ground-based observatories like the South Pole Telescope, SPT. By mapping subtle temperature fluctuations in the CMB, researchers are testing theories of cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. These refined models help explain the universe's large-scale structure and offer new insights into the fundamental properties of the early cosmos. In the field of planetary science and exoplanet discovery, the collaboration between JWST and ESA's Plato mission is proving highly effective. Plato's broad sky survey capabilities identify Earth-like planets, which are then further studied by JWST for atmospheric composition. Recent discoveries include multiple exoplanets with atmospheres containing water vapor, carbon dioxide, and other molecules that could suggest the presence of habitable conditions. These findings are crucial as they increase the likelihood of finding life-sustaining environments outside our solar system. Ground-based technology is also enhancing these studies. The Extremely Large Telescope, YLT, which began operations this year, is using its 39-meter mirror to directly image exoplanets and analyze their atmospheres. The YLT's adaptive optic systems provide the clarity needed to detect subtle atmospheric changes, such as biosignature gases like methane and oxygen, which are indicators of potential life. These observations are essential for advancing our understanding of exoplanets and refining the criteria for habitability. On the frontier of human space exploration, NASA's Artemis program continues to make strides with Artemis 3 preparing for launch. This mission, which aims to land astronauts on the Moon's South Pole, is focused on testing technologies for sustainable lunar habitation. These technologies include systems for extracting water ice from the lunar surface to produce oxygen and fuel, essential for supporting long-term human presence and preparing for future Mars missions. The Lunar Gateway Project, a collaborative effort among NASA, ESA, Roscosmos, and other international agencies, is set to play a critical role in these missions. Orbiting the Moon, the Gateway will serve as a platform for science and technology testing, as well as a staging point for deeper space missions. Its laboratories will focus on understanding the effects of microgravity, radiation exposure, and the logistics of interplanetary travel, crucial research for future missions to Mars and beyond. Mars exploration remains a priority, with the Mars Sample Return mission advancing through international cooperation. The Perseverance rover continues to collect and cache samples from the Martian surface, aiming to provide direct evidence of ancient microbial life. These samples, once returned to Earth, will be analyzed using the most advanced techniques available, potentially confirming whether Mars ever hosted life. Such a discovery would revolutionize astrobiology and pave the way for future human missions to Mars. The exploration of the outer solar system's icy moons is also advancing. The Europa Clipper mission, scheduled for launch later this decade, is designed to explore the subsurface ocean of Jupiter's moon Europa by flying through water vapor plumes erupting from its surface. By analyzing the composition of these plumes, the Clipper aims to detect organic compounds and other signs of hydrothermal activity, critical indicators of the potential for life. This mission builds on earlier findings from the Galileo and Cassini missions and could confirm the habitability of ocean worlds beyond Earth. The search for intelligent life is expanding with the capabilities of the Square Kilometre Array, SK. This telescope array, the largest and most sensitive ever constructed, monitors vast areas of the sky for technosignatures, signals that might indicate advanced civilizations. SK's comprehensive survey capabilities significantly enhance the chances of detecting such signals, making it a central component in humanity's ongoing effort to understand whether we are alone in the universe. Lastly, the study of gravitational waves continues to provide unprecedented insights into the universe's most energetic phenomena. The LIGO-Virgo-Cassegrain network, operating with enhanced sensitivity, has detected new types of wave events, including mergers between black holes and neutron stars. These observations offer direct evidence of how these massive collisions shape the cosmos and generate the heavy elements essential for planets and life. The data also test the limits of general relativity under extreme conditions, expanding our understanding of fundamental physics. The astronomical advancements of 2024 highlight an era of exploration and discovery unprecedented in scope. From mapping dark matter and studying early cosmic structures to preparing for lunar bases and Mars missions, each effort not only expands our scientific knowledge, but also lays the foundation for the next wave of human exploration. The continued collaboration between international space agencies and the integration of cutting-edge technologies ensure that the coming years will be marked by even greater revelations and progress. As we continue to explore the astronomical developments of 2024, advancements in technology, observation techniques, and space exploration missions are revealing new aspects of the universe and enhancing humanity's capabilities beyond Earth. This year has been a landmark period for expanding our understanding of cosmic structures, the early universe, and the search for extraterrestrial life. The James Webb Space Telescope, JWST, continues to play a pivotal role in deepening our knowledge of the early universe. By capturing the most detailed images yet of galaxies forming within the first few 100 million years after the Big Bang, JWST has allowed astronomers to observe rapid star formation rates and the enrichment of interstellar material with heavy elements. These findings challenge the current understanding of galaxy evolution, showing that these early galaxies formed and grew faster than expected, prompting the need for revised models of star and galaxy formation. Further investigation into these galaxies has revealed hints of population 3 stars, the first generation of stars thought to have formed from primordial hydrogen and helium. The indirect signatures captured by JWST, such as specific patterns in the chemical composition of these galaxies, suggest that these massive, short-lived stars played a crucial role in the early enrichment of the universe with heavier elements. If confirmed, these observations would provide a direct link between the first stars and the development of the complex structures we see in the universe today. Meanwhile, efforts to map the distribution of dark matter and dark energy continue to yield significant results. The Euclid mission, in tandem with the Dark Energy Spectroscopic Instrument DESI, has been mapping the cosmic web, the vast network of galaxies and dark matter that fills the universe. By studying how light bends around dark matter through gravitational lensing, Euclid has created detailed 3D maps that offer insights into how dark matter influences the growth and clustering of galaxies. These observations are refining our models of cosmic evolution, revealing that the distribution and behavior of dark matter may be more complex than previously understood. Simultaneously, DESI's measurements of the expansion rate of the universe help astronomers investigate dark energy's role in this process. DESI's comprehensive spectroscopic data allows for a more precise understanding of how galaxies are distributed and how dark energy might vary over cosmic time. This data is essential for testing whether dark energy behaves as a constant force or if it evolves, which has profound implications for the future of the universe. The hunt for habitable exoplanets and signs of life has accelerated with JWST and ESA's Plato mission working in unison. Plato's wide-field survey capability identifies Earth-sized exoplanets in habitable zones, while JWST's advanced spectroscopic tools analyze their atmospheres. Recent discoveries include several exoplanets with atmospheres rich in water vapor and organic compounds, increasing the likelihood of finding environments capable of supporting life. These combined observations refine our criteria for habitability and help focus future missions on the most promising targets. Ground-based observatories like the Extremely Large Telescope, YELT, have further enhanced these studies. The YELT's 39-meter mirror and cutting-edge adaptive optics provide clarity that rivals space-based observatories. This technology enables astronomers to image exoplanets directly, studying their atmospheric composition to detect biosignatures such as methane and oxygen. The YELT's capabilities are critical for confirming whether these biosignatures are indeed indicative of life or result from geological or atmospheric processes. Human space exploration is another area where 2024 has seen significant advancements. NASA's Artemis 3 mission, scheduled to land astronauts on the Moon's South Pole, focuses on testing and implementing sustainable technologies for long-term lunar habitation. This mission will explore and use lunar resources, such as extracting water ice to create oxygen and fuel, essential for supporting longer missions and preparing for Mars exploration. The Lunar Gateway Project, an international initiative involving NASA, ESA, Roscosmos, and others, is crucial in supporting lunar operations. Orbiting the Moon, the Gateway serves as a research platform and logistics hub for crewed lunar missions and future Mars expeditions. Its laboratories will focus on radiation shielding, life support, and the effects of long-duration space travel, providing critical information for human expansion deeper into the solar system. Mars exploration remains a priority as the Mars Sample Return mission progresses through the collaboration between NASA and ESA. The Perseverance rover continues to collect and cache samples from Mars' Jezero crater, which is believed to have hosted liquid water and potentially life billions of years ago. The mission's objective is to return these samples to Earth, where they will undergo detailed analysis to detect any signs of past microbial life, offering a historic breakthrough if confirmed. In the outer solar system, NASA's Europa Clipper mission is gearing up to explore Jupiter's moon Europa, one of the most promising locations for finding life beyond Earth. The Clipper will fly through plumes of water vapor emanating from Europa's icy surface to collect and analyze samples for organic molecules and other signs of hydrothermal activity. If successful, these findings could confirm that the subsurface ocean of Europa possesses the necessary conditions to support microbial life, bolstering the case for the habitability of ocean worlds. The search for intelligent extraterrestrial civilizations is expanding with the Square Kilometer Array, SK. The SK's unparalleled sensitivity allows it to scan vast regions of the sky for technosignatures, radio signals that might indicate advanced civilizations. By monitoring a wide spectrum of frequencies across an immense area, SK significantly enhances the likelihood of detecting such signals, making it a critical tool in humanity's ongoing effort to find out if we are alone in the universe. Gravitational wave astronomy has also advanced significantly, thanks to the upgraded LIGO-Virgo-Cagra network. These observatories have detected several new wave events, including rare collisions between neutron stars and black holes. These observations provide valuable insights into the most extreme environments in the universe and the production of heavy elements during these cosmic mergers. The data also continues to test general relativity's predictions, refining our understanding of how gravity behaves in such extreme conditions. The astronomical achievements of 2024 reflect a period of dynamic growth and discovery. From mapping the distribution of dark matter and studying early cosmic structures to preparing for sustainable lunar bases and Mars missions, each advancement contributes to a broader understanding of the cosmos and humanity's role in exploring it. As international collaboration deepens and technology evolves, the next wave of missions promises to further illuminate the mysteries of the universe, guiding humanity toward a future where space exploration and discovery are limitless. As we progress further into 2024, the field of astronomy continues to make monumental strides, with a focus on unraveling cosmic phenomena, enhancing human space capabilities, and refining the search for habitable worlds. The advancements and discoveries this year are not only expanding our scientific understanding, but also setting the groundwork for future space missions and collaborations that may redefine humanity's role in the cosmos. A significant area of research remains the study of the early universe and the formation of its first structures. The James Webb Space Telescope, JWST, has delivered new insights into the rapid formation of galaxies shortly after the Big Bang. By observing light from galaxies formed less than 1 billion years after the universe's inception, JWST has revealed that star formation rates and the buildup of heavy elements were faster and more widespread than previously modeled. This suggests that the early universe may have been more hospitable to star and galaxy formation, possibly due to the rapid cooling and condensation of gas clouds facilitated by dark matter. These observations are further supported by findings that hint at the presence of population 3 stars, the first generation of stars to form in the universe. JWST has detected the chemical signatures indicative of such stars in ancient galaxies, suggesting that they played a key role in creating the heavier elements necessary for later star and planet formation. Confirming the existence of these stars provides a crucial link in understanding the timeline of cosmic evolution and the transition from a universe dominated by simple elements to one with complex chemistry capable of supporting life. Efforts to map dark matter and dark energy continue with the Euclid mission and DESI. By observing the gravitational lensing effect, where dark matter bends the light from distant galaxies, Euclid has created highly detailed 3D maps of dark matter distribution. These maps are crucial for understanding how dark matter influences the formation of cosmic structures, revealing patterns and clustering behaviors that are leading to revisions in our models of galaxy formation. DESI's focus on measuring the light spectra from millions of galaxies adds to this effort, providing data that helps determine how galaxies are distributed across vast distances and how dark energy drives the universe's expansion. The data collected so far shows that dark energy's influence may not be uniform throughout cosmic history, suggesting that its properties could evolve over time, a finding that has significant implications for the fate of the universe. The search for exoplanets and signs of life has also taken a major leap forward. The collaboration between JWST and ESA's Plato mission is identifying Earth-sized planets within the habitable zones of their stars. Once Plato detects these planets through transit observations, JWST analyzes their atmospheres for critical molecules such as water vapor, carbon dioxide, and methane. This partnership has led to the discovery of multiple planets with atmospheres that could support life, making these worlds prime candidates for further investigation. On the ground, the extremely large telescope, YELT, is enhancing these efforts by offering direct imaging of exoplanets and their atmospheres. With its powerful adaptive optics, the YELT can capture the faint light from distant planets, allowing for a detailed study of their atmospheric compositions. This capability is essential for detecting potential biosignatures like oxygen and methane, which are considered strong indicators of life if found together in the right proportions. Such observations are helping to build a catalog of planets where conditions might be similar to early Earth. In terms of human space exploration, 2024 marks a critical year for advancing lunar and Martian missions. NASA's Artemis 3 mission is on track to land astronauts on the Moon's South Pole, a region rich in water ice deposits. The mission will focus on demonstrating technologies for in-situ resource utilization, such as extracting water from lunar ice to create oxygen and fuel. This technology is vital for establishing a sustainable human presence on the Moon, which serves as a testbed for future Mars missions. The Lunar Gateway, a multi-agency space station that will orbit the Moon, is integral to this effort. As a collaborative project involving NASA, ESA, Roscosmos, and others, the Gateway will provide a platform for scientific research, technology testing, and crew staging for lunar and interplanetary missions. It will enable studies on the effects of long-duration space travel, radiation protection, and advanced life support systems, ensuring that the lessons learned from lunar missions are applicable to future missions to Mars. Mars exploration is advancing through the Mars Sample Return Mission, a collaboration between NASA and ESA. The Perseverance rover, currently active in Mars' Jezero crater, continues to collect samples that are being cached for retrieval. These samples aim to provide definitive evidence about Mars's habitability and the presence of ancient microbial life. If signs of life are detected, it would mark one of the most significant discoveries in history, transforming our understanding of the conditions necessary for life. Beyond Mars, the exploration of ocean worlds such as Europa and Enceladus is gaining momentum. NASA's Europa Clipper mission, set to launch later this decade, will study the plumes of water vapor erupting from beneath Europa's icy crust. The mission's goal is to detect organic molecules and signs of hydrothermal activity, which could indicate the presence of life. This mission, alongside ESA's JUICE mission targeting Ganymede, is part of a broader effort to investigate the habitability of moons with subsurface oceans, environments considered some of the best places to find life beyond Earth. In the search for intelligent extraterrestrial civilizations, the Square Kilometer Array (SK) has begun its ambitious survey of the Milky Way and beyond. With its unprecedented sensitivity, the SKA can monitor vast regions of the sky for technosignatures, radio signals, or other artificial emissions that might indicate the presence of advanced civilizations. This large-scale effort significantly increases the chances of detecting such signals, making SKA a central tool in humanity's quest to determine if we are alone in the universe. Gravitational wave astronomy has also seen breakthroughs, thanks to the enhanced capabilities of the LIGO-Virgo-Cagra network. This year, the network has detected several new events, including the mergers of black holes with neutron stars. These observations provide valuable insights into the processes that create the universe's heaviest elements and allow astronomers to test theories of gravity under the most extreme conditions. Such data continues to refine our understanding of the cosmos and the nature of space-time itself. Overall, the achievements of 2024 demonstrate the interconnected nature of astronomical research, where space missions, ground-based observatories, and international collaborations work together to expand humanity's reach into the cosmos. From probing the universe's earliest galaxies and mapping dark matter to exploring planets and moons for signs of life, each advancement lays the groundwork for the future. As technology continues to evolve, the coming years promise even more profound discoveries, ensuring that humanity's journey into space and exploration of the universe will be transformative and expansive. As we continue into the latter part of 2024, the astronomical and space exploration advancements remain remarkable, further unraveling the mysteries of the universe and expanding human capabilities beyond Earth. From black hole dynamics to the refinement of human missions, this year has been transformative, marked by cutting-edge technologies and international collaboration. One of the most groundbreaking areas of research remains the detailed study of black holes, particularly through the combined capabilities of the James Webb Space Telescope, JWST, and the Event Horizon Telescope, EHT. Recent observations of the supermassive black hole at the center of the Milky Way, Sagittarius A*, have provided higher resolution images, capturing the accretion disk and the complex dynamics of magnetic fields surrounding it. These images confirm that magnetic fields play a pivotal role in channeling matter into black holes and launching relativistic jets, streams of particles moving close to the speed of light. Simultaneously, JWST has targeted intermediate mass black holes, IMBHs, which are thought to be the missing link between stellar mass and supermassive black holes. Observations of globular clusters suggest the presence of these IMBHs through the motion of stars and the influence of unseen massive objects. Confirming their existence helps fill a critical gap in understanding how supermassive black holes form and grow over cosmic time. Cosmic evolution studies have also intensified, particularly with the mapping of the universe's structure through the Euclid mission and the Dark Energy Spectroscopic Instrument, DESI. These missions work together to provide the most comprehensive maps of the cosmic web ever created, revealing how dark matter shapes galaxies and influences cosmic expansion. Euclid's data on gravitational lensing has allowed for precise mapping of dark matter's distribution, while DESI's spectroscopic analysis enhances our understanding of dark energy's role in this process. Initial findings suggest that the behavior of dark energy might vary over time, offering new insights into whether the universe will expand indefinitely or eventually collapse. These missions also enhance our understanding of the large-scale structure of the universe, known as the cosmic web, a vast network of filaments and voids composed of galaxies and dark matter. This structural framework is crucial for studying how galaxies evolve and cluster. Observations show that the influence of dark matter is more complex and dynamic than previous models suggested, prompting astronomers to refine their simulations. In the search for exoplanets, JWST and ESA's Plato mission continue to be instrumental. Plato has identified numerous Earth-sized exoplanets in habitable zones, and JWST has confirmed the presence of water vapor, methane, and carbon dioxide in the atmospheres of several of these planets. Such discoveries are crucial, as they point to potentially habitable environments beyond Earth. By combining data from these missions, scientists can prioritize planets with atmospheres most similar to Earth's for further study. The Extremely Large Telescope, YELT, has further advanced the study of these exoplanets. Its ability to directly image distant planets and analyze their atmospheres in detail allows for the detection of potential biosignatures, molecules that might indicate biological processes. The YELT's use of adaptive optics to counteract atmospheric distortions ensures that these observations are of the highest precision, making it one of the most powerful tools in the search for extraterrestrial life. In human space exploration, the Artemis program is on track for its historic mission. Artemis 3 is set to land astronauts on the Moon's South Pole, an area rich in water ice. This mission will demonstrate crucial technologies for in-situ resource utilization, such as extracting and processing water ice to produce oxygen and fuel. The goal is to establish a sustainable lunar presence, which will act as a testbed for future Mars missions and long-duration human exploration beyond Earth. The Lunar Gateway, an international space station orbiting the Moon, continues to develop as a cornerstone of this strategy. The Gateway will serve as a research and logistics hub for lunar and Mars missions, offering facilities for studying the effects of long-term space travel on the human body and testing advanced life support and radiation shielding technologies. Its role in supporting sustainable lunar exploration and as a launching point for deep space missions underscores the importance of international cooperation in space. Mars remains a focal point of exploration, with the Mars Sample Return mission progressing steadily. The Perseverance rover is actively collecting samples from Jezero Crater, an ancient lakebed that could hold evidence of past life. This mission, a collaborative effort between NASA and ESA, aims to bring these samples back to Earth for detailed analysis, potentially confirming whether life once existed on Mars. Such a discovery would be a milestone, fundamentally reshaping our understanding of life's distribution in the universe. Beyond Mars, the exploration of icy moons like Europa and Enceladus is gaining traction. The Europa Clipper mission is set to investigate the subsurface ocean of Jupiter's moon Europa by analyzing the water vapor plumes emitted from its icy surface. The mission aims to detect organic molecules and other chemical signatures that might indicate hydrothermal activity, a key ingredient for life as seen on Earth. These findings would strengthen the case for ocean worlds being the most promising locations for finding life beyond Earth. The search for intelligent extraterrestrial civilizations continues with the Square Kilometre Array, SK, the world's most powerful radio telescope. The SK's immense sensitivity and ability to scan a wide range of frequencies make it an unparalleled instrument for detecting technosignatures, signals that could indicate advanced alien technologies. Its ability to monitor vast regions of space increases the likelihood of discovering such signals, making the sky central to humanity's quest to answer the question of whether we are alone in the universe. In the realm of gravitational wave astronomy, the LIGO-Virgo-Cagra collaboration has achieved new milestones. These observatories have detected mergers of black holes and neutron stars, providing valuable data on the nature of these collisions. Such events not only help us understand how elements like gold and platinum are formed, but also test the limits of Einstein's theory of general relativity. The precision and sensitivity of these detectors are expected to reveal even more about the universe's most energetic and mysterious phenomena. In summary, the developments in 2024 represent a dynamic period for astronomy and space exploration, showcasing humanity's growing capability to explore the universe. From refining our understanding of the early cosmos and dark matter to preparing for sustainable lunar bases and Mars missions, each achievement lays the groundwork for the future of space discovery. The international collaboration and technological innovation driving these efforts promise that the coming years will bring even more revolutionary insights, expanding our reach and understanding of the universe like never before. The search for extraterrestrial life has long been one of the most captivating quests in human history. From ancient myths about gods from the skies to modern-day theories about life on Mars, the idea that we are not alone in the universe continues to spark curiosity. In recent years, however, this speculation has moved beyond the realm of science fiction into a more scientific and methodical investigation. The discovery of thousands of exoplanets orbiting distant stars, along with new advancements in technology, has opened up possibilities for finding life in places we previously thought uninhabitable. But as we refine our search, scientists are starting to focus on new, unexpected areas that might harbor life, not just on planets but in far more unusual environments. One of the more intriguing developments has been the rising interest in rogue planets. These are planets that don't orbit a star, but instead drift through space, cold and dark, seemingly detached from any solar system. For decades, such objects were considered too inhospitable to sustain life. But recent models suggest that rogue planets could potentially retain heat in their cores for billions of years, allowing subsurface oceans to exist. These oceans, shielded from the harshness of space by thick layers of ice, might just be the ideal places for microbial life to thrive. This hypothesis challenges our conventional thinking about the need for sunlight and positions rogue planets as potential candidates in the ongoing search for life beyond Earth. Another fascinating frontier in this search involves the exploration of Saturn's moons, particularly Titan and Enceladus. Titan is unique in that it has lakes and rivers, not of water, but of liquid methane and ethane. Methane-based life forms, if they exist, would represent an entirely new branch of biology. On the other hand, Enceladus presents an even more exciting prospect. Beneath its icy crust lies a global ocean, and geysers at the moon's south pole spew water vapor, organic molecules, and other chemicals that indicate a complex, dynamic environment. These discoveries have led to the theory that microbial life could be flourishing deep within Enceladus Ocean, living off the chemical energy provided by hydrothermal vents on its seafloor. The recent launch of the James Webb Space Telescope, JWST, marks a monumental leap forward in our ability to probe these distant worlds. With its unprecedented sensitivity, the JWST is capable of analyzing the atmospheres of exoplanets in detail. By studying the light that passes through these atmospheres, scientists can detect the presence of gases that might indicate life, such as oxygen, methane, and water vapor. In fact, in its early mission, the JWST has already detected carbon dioxide on an exoplanet, a promising sign that the detailed study of exoplanetary atmospheres is going to yield groundbreaking results. This next phase of exploration is no longer confined to simply identifying exoplanets, but rather evaluating them as potential abodes for life, based on their chemical fingerprints. Astrobiologists are also beginning to broaden their definition of what constitutes a habitable planet. Traditionally, the search for life focused on planets within the habitable zone, the region around a star where liquid water could exist. However, as we uncover more about the diversity of life on Earth, particularly extremophiles, organisms that thrive in extreme conditions. The range of possible life-bearing environments has expanded. Organisms have been found living in the most inhospitable environments on Earth, miles beneath the ocean's surface, in acidic hot springs, and even in radioactive waste. This has prompted scientists to reconsider the notion that life requires Earth-like conditions. Planets or moons once deemed too hostile for life are now being reconsidered, thanks to the realization that life is incredibly adaptable. In fact, the discovery of extremophiles has had a profound impact on how we think about potential life forms on Mars. While the surface of Mars is dry, cold, and bombarded by radiation, evidence suggests that liquid water once flowed on its surface and that underground reserves of briny water may still exist. The idea that microbial life could be surviving underground, protected from the harsh surface conditions, has reinvigorated interest in the red planet. Future missions, such as the Mars Sample Return mission, aim to bring back Martian soil samples, which could contain clues to whether life ever existed or still exists on Mars. Beyond Mars, the search for life has extended to the distant reaches of our own solar system. Jupiter's moon Europa has long been a focus of interest due to its icy crust and potential subsurface ocean. Similar to Enceladus, Europa's ocean might be warmed by hydrothermal activity, making it a candidate for life. Upcoming missions like NASA's Europa Clipper are set to explore the moon's surface and measure the thickness of its ice, potentially revealing more about the habitability of this intriguing world. The idea of life thriving in environments once considered extreme or hostile has led to another surprising theory: the possibility that life could exist in the clouds of Venus. Venus, with its surface temperatures hot enough to melt lead, seems like one of the last places one would expect to find life. However, in 2020, scientists made headlines when they detected phosphine gas in Venus' atmosphere, a potential biosignature. While the presence of phosphine is not definitive proof of life, it raises intriguing questions. Could microbial life exist in the relatively cooler, cloud-covered regions of Venus' atmosphere, floating in droplets of sulfuric acid? Further investigations are underway to confirm whether this phosphine detection is a sign of life or if there are other, non-biological processes that could explain its presence. Another area of growing interest is the potential for life to exist in even more exotic environments, such as on super-Earths or water worlds. Super-Earths are planets larger than Earth, but smaller than gas giants, and they are one of the most common types of exoplanets discovered. Some super-Earths may have thick atmospheres and deep oceans, possibly creating conditions where life could flourish. Water worlds, which are planets entirely covered by oceans, also offer exciting possibilities. These planets, if they exist in the right conditions, could support vast ecosystems beneath their deep waters, shielded from cosmic radiation and other hazards by their thick atmospheres and oceans. Even the study of stars themselves is contributing to our understanding of where life might exist. A relatively new area of research involves studying the impact of stellar flares on planetary atmospheres. Red dwarf stars, which are the most common type of star in our galaxy, often produce powerful flares. These flares can strip away the atmosphere of planets orbiting too closely, but they could also trigger chemical reactions that might help create the building blocks of life. The interplay between stellar activity and planetary atmospheres is an area that requires further study, but it highlights how complex the conditions for life can be and how many factors need to be considered when determining a planet's habitability. As we push the boundaries of where we think life could exist, we are also reconsidering the way we communicate with potential extraterrestrial civilizations. For decades, efforts like the Search for Extraterrestrial Intelligence, SETI, have focused on listening for radio signals from distant civilizations. But what if alien civilizations use forms of communication we haven't even thought of yet? Some scientists suggest that instead of focusing solely on radio waves, we should also consider looking for other types of signals, such as laser pulses or even neutrinos, particles that pass through matter almost undisturbed. These alternative methods of communication may be the key to detecting signals from technologically advanced civilizations that have developed beyond the capabilities of radio. The quest to find extraterrestrial life is no longer just a matter of idle curiosity. It is a scientific pursuit with real implications for our understanding of biology, chemistry, and the nature of life itself. As we continue to explore our solar system and beyond, we are on the verge of potentially answering one of the most profound questions humanity has ever asked. Are we alone in the universe? Each new discovery brings us closer to that answer. And while we have yet to find definitive proof of life beyond Earth, the growing body of evidence suggests that we may be on the right track. The next few decades promise to be a thrilling time for astrobiology and space exploration. With upcoming missions to Europa, Titan, and beyond, as well as the expanding capabilities of telescopes like the James Webb, we are poised to make discoveries that could reshape our understanding of life in the universe. Whether it's through the discovery of microbial life on a distant moon or the detection of a signal from an alien civilization, the search for extraterrestrial life is just beginning, and the possibilities are endless. As we continue to expand our understanding of where life could exist, a new and revolutionary idea is emerging in astrobiology. The possibility of life existing in environments powered not by sunlight, but by alternative energy sources entirely. This concept challenges our deep-rooted assumption that a star's energy is essential for life, pushing the boundaries of what we consider habitable environments. One of the most interesting developments in this area is the study of dark biospheres. These are ecosystems that exist in total darkness, relying on energy sources other than the sun. On Earth, we already have examples of such systems, like those found deep in the ocean around hydrothermal vents. Here, entire ecosystems thrive without sunlight, relying on chemosynthesis, a process where organisms generate energy from chemical reactions involving sulfur, methane, or other compounds. The discovery of these ecosystems has fundamentally altered our perception of what life needs to survive and has opened the door to considering similar systems on other planets and moons. In particular, I see moons like Europa and Enceladus, both known to have subsurface oceans, are prime candidates for housing dark biospheres. The thick ice shells of these moons block sunlight from reaching their oceans, but the heat generated from tidal forces and potential hydrothermal activity could provide the necessary energy for life to exist. If such ecosystems do exist, they would likely be similar to the deep-sea hydrothermal vent communities found on Earth, relying on chemical energy rather than solar energy to sustain themselves. This shift in thinking has expanded the search for life in the solar system, allowing scientists to target environments previously deemed inhospitable. Another fascinating development comes from studying the potential for silicon-based life. Earth's life forms are carbon-based, relying on carbon's ability to form long, stable chains that serve as the backbone for complex molecules like DNA and proteins. However, silicon, an element abundant in the universe, shares many chemical properties with carbon and could theoretically form the basis for life under the right conditions. Silicon-based life forms might exist in environments that are radically different from Earth's, such as planets with extreme temperatures or high-pressure atmospheres. While no definitive proof of silicon-based life has been found, the idea continues to be explored as we seek to broaden our understanding of life's potential diversity. These new theories are not limited to single planets or moons. As we move forward in the search for extraterrestrial life, scientists are also considering the possibility of interstellar panspermia, the idea that life might not be confined to a single world but could spread across star systems via comets, asteroids, or other spacefaring objects. This theory suggests that life could be more common than previously thought, as it might be transferred from one celestial body to another, potentially spreading throughout entire galaxies. This raises the question: could Earth itself be the product of panspermia? Some researchers speculate that the building blocks of life could have been brought to Earth by comets or meteorites, seeding our planet with the essential components for life. As we consider the implications of panspermia, a new wave of research is focusing on the search for biosignatures in the interstellar medium, the vast stretches of space between stars. In 2023, a groundbreaking discovery was made when organic molecules, including a precursor to RNA, were detected in a molecular cloud 450 light-years from Earth. This finding suggests that the basic ingredients for life may be widespread in the universe, present even in the cold, empty void of space. Such discoveries fuel the idea that life, or at least the potential for life, could be far more common than we have imagined. The ongoing search for biosignatures, specific molecules or features that indicate the presence of life, has also expanded beyond traditional markers like oxygen or methane. Recent research suggests that we may need to look for more subtle, indirect signs of life, such as the presence of certain isotopic ratios, unusual chemical imbalances, or even the effects of biological activity on a planet's surface. For example, scientists are investigating the possibility that the presence of certain minerals or geological features could point to biological processes at work, even if direct evidence of life is absent. This approach broadens the scope of what we might consider a biosignature and could lead to breakthroughs in the detection of extraterrestrial life. In addition to new methods of detecting life, there are also new theories about how life might communicate across vast cosmic distances. As we continue our efforts to contact extraterrestrial civilizations through projects like SETI, scientists are considering the possibility that advanced civilizations might use forms of communication that are currently beyond our technological understanding. One such idea is that highly advanced civilizations might communicate using quantum entanglement, a phenomenon where particles become linked in such a way that the state of one can instantly affect the state of another, regardless of distance. While quantum communication is still in its infancy on Earth, it could represent a method by which extraterrestrial civilizations transmit information across the cosmos. On the subject of communicating with extraterrestrial life, an important ethical debate has arisen regarding whether we should actively attempt to send messages to potential alien civilizations. Some scientists warn that broadcasting our existence to the universe could be dangerous, as we cannot predict the intentions of any civilizations that might receive our signals. Others argue that the benefits of making contact with an advanced extraterrestrial civilization far outweigh the risks, potentially leading to an exchange of knowledge that could revolutionize human society. This debate continues to unfold, with no clear consensus on the best course of action. At the same time, we are gaining a deeper understanding of the potential technological capabilities of advanced civilizations through the study of Dyson spheres, hypothetical megastructures built around stars to capture their energy. The concept, originally proposed by physicist Freeman Dyson in 1960, suggests that an advanced civilization might build such structures to harness the immense energy output of its star. While no definitive evidence of Dyson spheres has been found, astronomers continue to search for signs of these or other large-scale, technological artifacts that could indicate the presence of extraterrestrial civilizations. As the search for life in the universe continues, one of the most profound implications is the possibility that we may soon discover that life exists in forms we cannot yet comprehend. If we find microbial life on Mars, Europa, or Enceladus, or if we detect signals from an advanced civilization in a distant galaxy, it will challenge our understanding of biology, technology, and our place in the cosmos. The discovery of extraterrestrial life would not only answer one of humanity's oldest questions, but also open the door to new philosophical and ethical considerations about our role in the universe. One of the most intriguing questions arising from the potential discovery of extraterrestrial life is how such a discovery would affect human society. While some people may embrace the idea with excitement and curiosity, others may experience fear or anxiety about the implications. Would discovering microbial life on another planet lead to a re-evaluation of our place in the universe? Could contact with an advanced civilization upend our societal structures and technological paradigms? These are questions that we may need to confront in the near future as our search for life beyond Earth intensifies. As we stand on the cusp of potentially transformative discoveries, it's important to recognize that the search for extraterrestrial life is not just a scientific endeavor, but a deeply human one. Our desire to understand whether we are alone in the universe speaks to our need for connection, exploration, and understanding of our own origins. Whether or not we ever make contact with an alien civilization, the search itself is pushing the boundaries of what we know about life, the universe, and everything in between. Each new discovery, no matter how small, brings us closer to answering the profound question, are we alone? For now, we continue to explore, to probe distant worlds, and to push the limits of our knowledge, knowing that each new piece of the puzzle might bring us closer to uncovering the truth about life and the universe. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe and see you on our next interstellar trip.